For every software developer, data structures are essential to their daily lives, helping them organize, store, and access information more efficiently. While data structures are primarily used in computer science and engineering, they can also be applied to many aspects of your daily routines. For example, shopping, personal organization, finance management, social networking, and many other areas of everyday life can be managed effectively using data structures. Data representation and manipulation can be done in a way that makes it simple for algorithms to operate with. The performance of your program can be enhanced, for instance, by selecting a data structure to store large amounts of data that needs to be frequently accessed or modified. Arrays, linked list, stacks, queues, trees, and graphs are some common data structures used. Each of these data structures has advantages and disadvantages, and selecting the appropriate one for your problem can significantly improve the efficiency and maintainability of your code. In fact, data structures are crucial tools for programmers and computer scientists since they aid in optimizing data storage and processing in various applications. On that note, hey everyone, welcome to Data Structure Full Course Part 1 video by Simplilearn. In this video, we'll begin with an introduction to data structures, followed by an explanation of an algorithm, and then we'll learn about data structures, pointers, and structures. Next, we'll move on to topics like arrays, linked list, types of linked list, and finally, the fundamental distinctions between arrays and linked list. Then, we'll dive into little advanced topics like stacks, queues, trees, and graphs, covering their various types of it in the next part. So without any further delay, let's get started. Over to our training experts.
Data is an information that has been translated into a form that is efficient to movement or processing in computing. As it relates to today's computers and transmission media, data is an information that has been converted into binary digital form. The term raw data refers to the data in its most basic digital format. After defining data, let's look at what data structure entails. A data structure is a data organization, management, and storage format in computer science that allows for efficient access and modification. Or, a data structure is an algebraic structure about data that contains a collection of data values, their relationships, and their functions or operations that can be applied to the data. We will now understand why exactly we need data structures now that we have already defined what is a data structure. So, let us have a look at some of the data structure characteristics. The first one is, each data structure allows data to be stored differently. Following that, the data structure allows for more efficient data search and retrieval. Then, specific data structures are chosen to solve specific problems. Last but not the least, it enables the management of large amounts of data such as large databases and indexing services such as hash tables. Let us now look at some real-world examples of data structures. First and the foremost, we have the dictionary. Assume that we are looking for the word Simplilearn in the dictionary. And we know it begins with the letter S. So we can search for this word beginning with the letter S, and then this is an example of array data structure. As a result, this dictionary can also function like an array data structure. Following by that, we have a music player example. If you have a playlist with 3 songs, the second song will play after the first and the third will play after the second. So these will be played without any interruption because all these 3 songs are linked with each other using linked list type of data structure. So followed by linked list, the next example we have is the data structures. The stack of books analogy is a perfect example of the real-time working of the stack data structure. Subsequent to that, assume there is a line of people at a ticket window and the person who comes first gets the ticket. This particular movie window queue is an example for the real-time implementation of queue data structure. Last but not the least, Google Maps. Google Map is the graph data structure in which all the cities and states are connected. If we want to go from one place to another, there may be many ways to do so. So we can use some algorithms to find the shortest path. As a result, the Google Map is a perfect example for the graph data structure working analogy. Following that, we will look at some different types of data structures in this tutorial. So the first type is the linear data structure. The elements in the linear data structure are arranged subsequently one after the other. They are simple to implement because the elements are arranged in specific order. followed by the first type. The second type is the non-linear data structure, which we will be discussing a bit later. So in linear data structures, we have 4 different types. The first one is the array data structure. Memory elements are arranged in a continuous order in arrays, and arrays elements are of same type. The software program also determines the type of elements that can be stored in arrays. So followed by arrays, we have linked list. Linked lists are completely similar to data structures. Data elements in linked list data structure are linked together by a series of nodes. Furthermore, each node contains the data items as well as the address to the next node. The third data structure is the stack data structure. Elements in a stack data structure are stored using LIFO principle. In other words, the last element stored in the stack is removed first. In stack, operations can only be performed in one end, namely the top. And the last data structure is the queue data structure. Unlike stack, queue data structure operates in the FIFO principle, which states that the first element stored in the queue is removed first. In a queue, insertion and deletion are carried out from opposite ends. Now we will discuss the second type of data structures, which are the non-linear data structures. The non-linear data structure is the second type of data structure. Non-linear data structures do not have elements in any order as opposite to the linear data structures. Instead, they are arranged in hierarchical order, with one element connected to one or more others. So the first one in the nonlinear data structures is the tree data structure. A tree data structure is built using nodes and edges. Each element in the tree data structure is called as node or vertex. Each vertex or node is connected to the other nodes or other vertices using edges. And the second one in the list is the graph data structure. A graph data structure is completely like a tree data structure. It also has the vertices and edges. Each vertex in a graph data structure is connected using edges. The only difference between a tree and graph is that in tree you can have n number of vertices, but in graph you will have only 2 vertices. After discussing the graph data structure, we will move ahead into the last segment of this tutorial, that is importance of data structures. So the first one, data structures are widely used in almost every aspect of computer science, both for simple and complex computations. Next, data structures are used in all areas of computer science, including artificial intelligence, graphics, big data, operating systems, and much more. After that, the data structures are an essential component of many computer algorithms because they allow programmers to manage data efficiently. So how does algorithm work in real life? So we'll have a use case here. On my screen, we have a lady and she is Shreya. Shreya wants to make some tea, and for that she is following some steps. So the first step is, she'll take a pan and fill it with water and place it on a gas stove. Followed by that, the second step is, she'll make sure that the water comes to a nice boil, and then she adds some tea leaves and sugar. Followed by step 2, we have step 3, where she'll allow the leaf to be fully expanded and she'll add some milk after that. Next we have the step 4, where she will wait for the tea to come for a good decent boil. Next we have step 5, where she'll turn off the gas and she'll take the pan off from the stove and the tea is ready to get filtered. And lastly we have the step 6, where she is all set with the tea. So in computer science, an algorithm is a method or set of rules that we must be following to perform some specific calculations or other problem-solving operations. As a result, an algorithm is a collection of rules or instructions that govern how a work needs to be conducted step by step to achieve the desired results. To accomplish a task, we first provide some input and then follow a sequence of steps to acquire the required outcome of the input. So that is the fundamental definition of an algorithm, and we also had a use case. And now we will move ahead and understand the characteristics of algorithms. So basically we have 6 characteristics of algorithm. So the first one is, it should be clear and unambiguous. The second one is that it has to be well-defined inputs. And the third one is that it has to be having well-defined outputs as well. The fourth property of an algorithm is its feasibility. Followed by that, finiteness, and finally we have language independence. Now we will look into each one of the characteristics in detail. So first we have clear and unambiguous. So this statement is the one which states that the algorithm should be straightforward, simple and easily readable. Each one of its steps should be distinct in every way and lead it to a single conclusion. So the next one is, it should be having well-defined inputs. So this means that an algorithm should indicate what output can be expected, as well as the input should be properly well-defined. Now we have the third one. Similarly, we should also have well-defined outputs. So the well-defined output characteristics of an algorithm means that the algorithm must clearly indicate what output can be expected, as well as the output should also be well-defined. Followed by the third characteristic, we have the fourth characteristic, that is the finiteness of algorithm. So the finiteness of algorithm says that the algorithm must be finite and it must not result in infinite loops or similar situations. So followed by the fourth one, we have the fifth characteristic that defines about the feasibility of an algorithm. So feasibility of an algorithm states that the algorithm must be really simple, generic and practical. It must be able to be executed with resources available. Now the last characteristic of the algorithm is being independent of the language. So it means that the algorithm should be defined in such a way that it is completely independent of the language. It must be simple instructions that can be implemented using any programming language. So these were the 6 major characteristics of algorithm. Now let's move ahead and understand how to write an algorithm. Writing an algorithm does not have any hard and fast rules. Next, algorithms are never created to support a specific programming language. As we all know, algorithms should be capable enough to support the conditional statements such as if else, switch, etc. An algorithm should be capable enough to execute some of the conditional statements such as if else, switch, etc. And also it must be capable to execute the iterative statements such as for loop, while loop, do while loop, etc. We usually create algorithms in a step-by-step manner. However, this isn't always the case. After the problem domain has been well defined, algorithm writing is a procedure that is carried out. We build an algorithm to find a solution to a problem. A problem can be resolved in a variety of ways. Let's look at an example of how to write an algorithm. Consider the following scenario. We need to create an algorithm to determine the largest number among the 3 given numbers x, y, and z. As a result, the initial solution to the problem can be written in this manner. So we begin with reading all the 3 numbers, and in the second step we will have a condition that says if x is greater than y, we will proceed to step 4, else we will proceed to step 5. Next, in step 4, we establish a condition that if x is greater than z, then x is the largest of the 3 numbers. Otherwise, z is the largest. If y is greater than z, z will be the greatest number. Otherwise, y will be the largest number amongst all the 3 in step 5. And the procedure will be terminated. Let's have a look at what the next solution has to offer. In this algorithm, we begin by reading all the 3 variables, then compare all the 3 numbers in the third step to determine the largest number, which is if x is greater than y, then there is another if-else statement that states that if x is greater than y, then x is largest, otherwise z is the largest. Then there's if-else statement which says that if y is greater than z, then y is greater, otherwise z is the greatest of the 3 numbers. So this is how we have multiple solutions to the same problem. So after discussing these solutions, we will move ahead and understand algorithm analysis. The algorithm may be studied in 2 levels. First, before it is made, and then after it is created. The 2 analyses of an algorithm are as follows. The first one is priori analysis and the second one is the post analysis. So first we will talk about the priori analysis. Priori analysis refers to the theoretical analysis of an algorithm performed before its implementation. Before implementing the algorithm, other parameters such as processor speed might be considered, which does not affect the implementation component. Next, we will talk about post-analysis. A practical analysis of an algorithm is called as posterior analysis, and it utilizes any computer language to build the algorithm. The purpose of this analysis is to determine how much time and space the algorithm takes to operate. Now, after being understood the algorithm analysis, we will be able to comprehend the algorithm complexity. Two methods can be used to assess the algorithm complexity. The first one is time complexity, which states that the amount of time required to finish an algorithm's execution is known as its time complexity. Followed by time complexity, the other one is the space complexity, which is calculated by the quantity of space required to solve a problem and produce an output of space complexity of an algorithm. Let's take a closer look at these complexities. Now we will begin with time complexity of an algorithm. The big O notation is used to express an algorithm's time complexity. The asymptomatic notation is used to depict temporal complexity of big O notation. The time complexity is mainly determined by counting the number of steps required to complete the task. Let's take a look at an example to understand this time complexity in a much better way. If we want to find out a multiplication of n numbers, we can do it by executing a loop from 1 to n, then calculating multiplication when the loop ends. Then multiplication holds the n numbers multiplication, and last we return the calculated multiplication. The loop statement's time complexity will be at least n, and when the number of n increases, the time complexity will also increase. While the code's complexity, that is, returns multiplication, will remain constant because its value is unaffected by the value of n, and it will obtain the result in every single step. Next, we will discuss about space complexity, which is expressed with big O notation, just as time complexity. These four items are stored in space complexity. It initially saves program instructions, then stores constant values, then stores variable values, and finally it keeps track of function cells, jumping statements, and so on. The sum of auxiliary space and input size is used to calculate space complexity. The extra space or temporary space used by an algorithm is referred to an auxiliary space. After learning about algorithm complexity, we will look at some of the algorithm's pros and cons. So let's start with the advantages of algorithms. Firstly, algorithms are easy to understand. Next, algorithms are step-by-step representation of a solution. And lastly, the problem is broken down into smaller bits or steps in an algorithm, making it easier for the programmer. Now, an algorithm also have various drawbacks, one of which being it takes long time to write, hence it is time consuming. Second con of the algorithm is algorithms make it harder to demonstrate branching and looping statements. So followed by the advantages and disadvantages of algorithms, we now enter into the final segment where we discuss the differences between algorithms and programming. So the first difference is that an algorithm is a type of programming. On the other hand, a program is more directly associated with the computer performing one or more tasks, but an algorithm is more of a notation, a technique for solving a problem. Now, let us discuss the second difference. An algorithm can be decoded or run by a human, whereas the program is only run or decoded by a set of compilers of the computer. Now, the third difference. Basically, an algorithm is a design of the solution to the problem. Here, we can only analyze the solution, but we can never run it. But whereas on the other hand, programming is completely a different ball game. Here, you can directly implement a certain phase or an entire program and test the programs and get an output. So the fourth and the last difference between an algorithm and programming is an algorithm is written using natural human vocabulary, whereas programs are written using any programming language such as C, C++, Java, Python, etc.
A pointer is a variable that points to an address of another variable. It is declared using a star symbol, also called asterisk. And then we allocate a memory of a variable to it. We can access a variable's address using the ampersand symbol in the same manner as the pointer declaration. Let's write a code. We will declare a variable a is equals to 5 and a pointer ptr. Then we will assign this variable a's value to pointer ptr. Now let's write a print statement to directly access the variable's value using variable name. Let's write another print statement to print the value of a using pointer. Let's try and execute this program. As you can see, we have successfully accessed variables value using both variable name and pointers. Let's get back to our slides. Now, let's discuss different types of pointers. First up, null pointer, void pointer, while pointer, and dangling pointer. Let's discuss these in details. First up, null pointer. It is a kind of pointer that points to a null memory. As you can see in the figure, here is a pointer which is pointing to a null memory. To get a better understanding, let's try a simple program in the code editor. Let's write a code. First we will declare a pointer var. Then we will assign its value to null. Now let's try to print this statement. Let's execute this. As you can see, since this pointer points to a null or nothing, that's why it doesn't print anything. Let's get back to our slides. Next, void pointer. When a pointer is created with data type void, then this pointer is called void pointer. If we want to print the variable's value, then we have to typecast this pointer to avoid any error. For better understanding, let's get back to the code editor and try it with a simple code. First, we will declare an integer variable a is equals to 5 and a void pointer ptr. Now we will assign address of a to pointer ptr. Let's write a print statement to print this pointer. Let's run this program. As you can see, we are getting an error. That's because we can't print a void variable. To print this, we have to typecast this variable to integer. Let's do this. We can typecast a variable like this. Now let's print this. As you can see, we can print it now. Let's get back to our slides. Next, while pointer. When we create a pointer but don't initialize it by assigning any memory to it, then this kind of pointer is called while pointer. These pointers can be very tricky. They can even cause a program failure or a segmentation fault. Let's get back to the code editor and try it with a simple code. First, let's declare a pointer ptr. But we will not assign it with any address. Let's write a print statement to print it. This time we will directly print it. Let's execute this. As you can see, we are not getting any results because there is no value assigned to it. Sometimes it may even show segmentation error. Let's get back to our slides. Next, dangling pointer. Let's suppose there is a pointer p which is pointing at a variable. Now, if we deallocate this memory using a free function, then this pointer will point at a free space or a non-existing memory. Then this pointer will become a dangling pointer. To get a better understanding of this pointer, let's try it with a simple code. Let's declare a pointer ptr. Here we will dynamically allocate memory using a malloc function. To do this, we will put int star in a bracket, then malloc function, then in another bracket we will put memory size to be allocated. Now let's declare a variable a and assign its address to the pointer. Now to make it a dangling pointer, we have to deallocate the memory of this pointer. We will use free function for that. Now let's write a print statement to print this pointer. Let's execute it. As you can see, since we have deallocated its memory, that's why it is pointing to nothing. Hence, it doesn't print anything.
Now let's begin by understanding what a structure is in C. As we all know, array is a collection of elements of the same data type. Similarly, a structure is a collection of elements with the same or different data types. For example, unlike an array, a structure can have members of different data types like int, float, char, etc. Now let's have a look at structure declaration in C. We use the struct keyword before the tag name to define a structure. Tag name is nothing but a structure name. Whatever is declared inside the struct curly brackets are members of the structure. Once the members are declared, the variable has to be created to access the members of the structure. Now let's see the example. We have struct keyword followed by student as a tag name, then a list of structure members. And they are name of type char, roll number and age of type int, and s1 as a structure variable. We can have a list of structure variables. Another way of structure declaration is we can declare structure variable outside the curly brackets by using struct keyword followed by a tag name and then declare variable list. For example, struct keyword, then student tag name and s1 as a variable name. In structures in C programming, we cannot assign values during the definition of a structure. It indicates the wrong way to the declaration. So now, let us try to understand the right way of assigning values to the structure members in C. To assign values to all the members of a structure and access, we use dot operator, also known as a period operator. Look at the syntax below to clearly understand how we access and assign the structure members. First, the structure variables followed by the dot operator and structure members. For example, s1 dot roll number is equal to 34, s1 dot age is equal to 18, and we make use of the string function strcpy to copy the name. Next, we have structure initialization in C. We can also initialize the structure variable. And to initialize, we can directly assign values of all the structure members inside the curly brackets with an assignment operator. For example, struct student s1 is equal to, inside the curly brackets, enter the values separated by comma operator. In this particular example, name is John, the roll number is 22 and the age is 18. Now that we know how to declare and initialize structure variables in C, let's see how the structure elements are stored in the memory. As we know, cat takes 1 byte of memory space. So, according to the size of the string, the characters will occupy in the memory. In structures, the memory is created once the structure variable is declared. As per this example, s1.name is a string, so that memory will be allocated and its base address will be obtained. For the s1 variable, the total memory allocated is 8 bytes. That is, 5 bytes for s1.name, 2 bytes for s1.roll number, and 2 bytes for s1.age. So I think you got a good understanding of how memory is allocated for the structure elements. Okay, so let us move on to the structure within structure in C. When a structure contains another structure as a member, it is known as a nested structure or structure within a structure. For example, let's consider a structure named student and another structure name as a date. In this example, a structure date acts as a member. So, a structure date has its own members and they are date, month and year of type int. And structure variable for date is doj. And the structure variable is initialized for both the members of the structure, that is name, admission number, age, date, month and year. Now let's execute a simple structure program.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
As you can see, in this particular program using the structure, we have initialized the variables and trying to print the values. And by using the dot operator, we are accessing the members of a structure. So now let's run it. And here we got an output, name, roll number and age of a student structure. In our next program using structure, we are using another way to declare variable and initialize the structure members. As you can see, we have declared variable outside the structure curly bracket. And inside the main function, we have initialized the structure members. So now let's run the program. So here we got the same output.
So to understand this, let's go through a simple concept. Let us imagine that we have some data and the data is related to students, right? So if we wanted to store the marks of individual students, then we had to declare a variable for each of the student. So you can see we have student 1, student 2, student 3, 4 and 5 and their individual scores. So the score 1 is assigned to student 1 and so on, with student 5 being assigned to score 5. So in the real time, this might be a little clumsy. We have here just 5 students, so that is okay. But what if we had 500 students or 5,000 students, right? That might be an issue. There we have to create some 500 or 5,000 variables and it would be a little tough to handle that, right? Even if we wanted to apply some operations collectively on all the variables, that might be a little tedious. So what if we had one variable which could store all the 5 students or 500 students or 5,000 students all together and make it really easy for us to apply some operations collectively on all the students, right? This sounds a little bit logical. So similarly, we do have a data structure which can do that, which can collectively store all the data elements in it as a single variable. And it will also help us to apply the operations which are logical or mathematical on all the variables and their values together as a whole. So that is the purpose why we had created arrays. That is the purpose why we needed arrays. So far we have understood what was the necessity for arrays. Now we will understand what exactly are arrays. So basically an array is a linear data structure that stores the elements in a sequential manner, one after the other. And when you declare an array, the variables will be stored one besides the other, that is adjacent to each other in a sequential order. Now let us understand how the array is represented by the compiler. Now the next part, that is the memory representation of arrays. Now let us imagine that we have declared an array which stores character type data. And another important point to remember about arrays, when you declare an array, it stores only a single data typed elements only. For example, here we have declared a character type array, right? So we cannot store integer type data or float type data in it. We only have to save character type array or character type elements in this particular array. So now let us imagine that we have created an array which is of character data type, and these are the elements which are A, R, R, A, Y. Now how does the compiler represent it in the form of memory? So when you create an array, these are found, that is the index values and the address. So basically compiler will select a block of memory and it has addresses to that block, and it can be anything. Right here we have 11, 12, 13, 14 and 15, and in real time it might be 1001, 1002, 1003, 1004, 1005. The main motto is assign a sequential block of memory, and this is the array and the elements are A, R, R, A, Y, and this particular one, which is the last one, is the index of the array. That is the position of the array for user. So using this index, you can access the elements in the array. More on that in the accessing part. So let us imagine that we wanted to access the element R. So how to access it? We might not know the address, right? In that instance, we will use the index. This is for R reference. So we will tell, I want the element from array index number 2. And then we'll have the ARR, R element. So in the practical form, this is how we use the index. Now let's continue with the lower bound and the upper bound. So the first initial location is called as the lower bound, and at the last or the max value of the array is called as the upper bound. Now let us jump into the next topic where we will understand the different types of arrays. So these are the different types of arrays: one-dimensional arrays and multi-dimensional arrays. In multi-dimensional arrays, we have two more types, that is two-dimensional arrays and three-dimensional arrays. So how are arrays different from each other, right? So the first one, we'll deal with the first one, that is the one-dimensional array. Now, how is an array declared as one-dimensional? For that, we need subscript. So one-dimensional array requires only one subscript to specify the number of elements in an array. So how is it actually represented? So here you can see an example right on my screen. So here is how a one-dimensional array looks like. So here we have the data type, that is integer data type, and marks is the name of the array, and this is the size of the array. And here the elements will be stored, and here it is the index value of the array. And remember, the index value of array always starts from 0. In the previous example, that was only for basic understanding, so I just started that with 1. In the practical way, the array index always starts from 0. So followed by the one-dimensional array, we will deal with the multi-dimensional arrays. In that, we have the following. The first one is the two-dimensional array, and the second one is the three-dimensional array. In the multi-dimensional arrays, we require more than one subscript. In the previous example, we had one-dimensional array, so the subscript is just 1, that is 10 columns, right? So we just had one single row and 10 different columns. But in the multi-dimensional arrays, we need multiple rows and multiple columns, right? So we need 2 subscripts for two-dimensional array and more than 2 subscripts for three-dimensional arrays. So first we have the two-dimensional arrays. The 2D array is organized in the form of a matrix which can be represented as a collection of rows and columns. So here is the example. As you can see on my screen, we have 3 columns and 3 rows. And we have 2 subscripts that define the number of rows and the number of columns and the elements in each and every row. So the 1, 2, 3 confines the first row, 4, 5, 6 confines the second row, and 7, 8, 9 will be the third row. Now similarly, we have 3-dimensional arrays. A 3D array is a collection of 2D arrays which consists of 3 subscripts: block size, row size, and column size. So here we have an example for that. So we have 3 subscripts. That is, the first one is block size, the second one is the row number, and the third one is column number. So this happens to be the first block, this happens to be the second block. And this is how a 3-dimensional array can be represented. Now we have the next stage where we will understand how to declare the arrays. And the syntax is right on my screen. You need to specify the data type of the array, which is integer, float, or character, any selection which you make. Followed by that, you need to select an array name for your array, and inside that, you need to declare the array size. And sometimes you can also eliminate the array size if you wanted to, have a dynamic array. And here is an example for that. You have integer data type, name of the array is example, and the array size is 6. So the compiler will allocate continuous memory block of 6 integer type blocks. So these are the few more methods to initialize the array. So here you can see integer data type, array name is A, element size is 5, and we have 5 elements. The method 2 is, remember I have said you can eliminate the size of the array, right? So here you can use this way as well, integer data type, array name A, and no size here, and you can directly declare the elements. And the method 3rd. So here you have the name of the array, size of the array, and you are allocating the elements to the individual memory locations. This is also another method to initialize array. And method 4 is using a for loop. You can just initialize a for loop and the I value will be stored in the array locations starting from 0. Now let us understand how to access the elements in an array. So to access the elements in an array, you need to specify the name of the array and memory block where you have that element that you want to access. So here we have an example which is integer data type, name of the array is xyz, and the element we wanted to access is 5. So here we have an example that is integer type array name is xyz, and it has the size 5. And now we wanted to access the first element in an array. That can be done using the first index, that is xyz of 0 index, that is the first element, and accessing the second element, and so on. xyz of 1 will be the second element, xyz of 2, 3, 4 will be the third, and fourth and fifth elements. Now let us understand some basic operations that can be performed on the array elements. So the following are the operations that can be performed on the array elements, that is the traversal, insertion, deletion, searching, and sorting. Now let us get into practical mode and try to execute some examples based on traversal of the array, insertion of an element into the array, deletion of an element from an array, searching for an element in an array, and sorting the complete array. So at first we'll carry out the traversal operation. So here we have an array that is A of 5 and the elements are 1, 2, 3, 4 and 5. Now we're going to use a for loop to traverse through this array and print all the elements sequentially. Now let us execute this code and see the output. So as you can see, the code got successfully executed and the elements, that is 1, 2, 3, 4 and 5 from the array A are printed sequentially. Now moving ahead, we'll try to execute some examples based on insertion of element into the array. So on my screen you can see an example for inserting an element into the array at the starting position of the array. Now let us try to execute this code and see the output. Don't worry about the codes. These code documents will be attached in the description box below and you will be able to have an access to it and run these codes in your personal laptop and get a better learning experience. Now you can see the code got successfully executed and now it is asking for the size of the array. Let's declare it as 5. And now let's enter the elements into the array. Now it is asking for the element to be added at the beginning of the array. Now we have 2, 3, 4, 5 and 6 existing in the array. Let's add the first element, 1, and there you go. The resultant array is 1, 2, 3, 4, 5 and 6. The element which we added at the ending, which is 1, is supposed to be in the first or the beginning part of the array, which is here at the first index location as planned. Now let's get started with another example on the insertion. Now let's try to insert an element at any given location as per the user's choice. So as you can see, we have a program on my screen, and running this program must help us to insert an element into any given location of the array. Now let's try to quickly run this program and see the output. So there you go. Enter the elements into the array. Let's enter 1, 3. Let's try to run this program and see the output. So there you go. The program got successfully executed and now the output is asking for us to tell it the number of elements in an array. Now let's say 4 elements. So now let's enter the 4 elements. 1, 3, 4, 5 and 6. Okay. So the 4 elements, which is 1, 3, 4, 5 are been inserted. Now it is asking for the location where you want to insert the element. Now let us insert it in the second location. Now let us set the value as 2 and there you go. The resultant array is 1, 2, 3, 4 and 5 and the element, which is 2, was supposed to be added in the second location and it has been successfully added. Now let's try to execute another example based on insertion where you will try to insert the element in the last position. Now this program on my screen will help us to add an element at the end of the array. Let's quickly run this program. Now it is asking for us to enter the 5 elements of the array. Let's enter that. Now it is asking to enter the element to be inserted. Now let us enter the element. And this element should be added at the end location as discussed. The resultant array is 1, 3, 5, 7, 9 and 11. Now let's continue with the deletion operation. Now the program on my screen is an example for deleting an element from the beginning position of an array. Now the program got successfully executed and it's asking for us to enter the size of the array. Let's enter the size as 5. And now let's enter the elements of the array, that is 1, 2, 3, 4 and 5. Now the element from the first location, that is 1, has been deleted and the resultant array is 2, 3, 4 and 5. Now the code on my screen will help you to eliminate the element from the ending location of an array. Now let's try to quickly run this program and see the output. So you can see that the program is successfully run and it is asking for us to enter the size of the array. Let's enter 4. Now let's enter the elements of the array, that is 1, 2, 3 and 4. Now after eliminating the last element from the array, that is 4, we have the resultant array, that is 1, 2 and 3. Now a little homework for you guys. Let's try to execute an example for deleting an element from any location of an array. This will be a homework. Now don't worry, try on your own, and if you don't get that, you can refer to the comment sections below where you have the code document attached in the description box and you can refer to it. Now let's continue with the next operation where we will search for a given element in the array. So you can see that on my screen we have an example which will help us to sort the elements in an array. Let's quickly run this. So there you go, the program got successfully executed and now it's asking for the array size. Let's enter 5 and now let's enter the elements in a random order. Now the resultant array should be sorted. So there you go. The array after being sort is, it's 2, 3, 5, 14 and 21. So there you go, the array got sorted. So now we have finished our practical session. Let's have a quick overview again. So traversal in an array is a process of visiting each element once. Traversal can be done by various means, that is by counting the array elements, printing the values sorted in the arrays, and sum of all elements present in the array, and many more. So this is how we traverse our array from the first location to the last location. Again, the insertion operation. Insertion in an array is the process of including one or more elements in an array, and it can be done at the beginning, at the end, and at any given index of an array, which we executed for all the three types of examples. Now next we have the deletion operation. So deletion operation or deletion of an element is a process of removing a desired element and reorganizing the array, and it can be done at the beginning, at the end, and at any given index. So we have executed the example for at the beginning and at the end, and the homework was at the given index. Don't worry if you don't figure it out, you can always refer to the example document which is mentioned in the description box below. Now the search operation. Searching is a process of finding a given value in the list of values, and it decides whether the search key is present in the array or not, and we have executed an example on that. And again, the sort operation, where we will sort the given array. If the given array is not in the default order or in a given order, that is ascending or descending, then we can sort the order of the array by the user's choice, given it is ascending order or descending order. Now in the next section of the tutorial, we will discuss the advantages of using arrays. So the first one is array stores multiple elements of same data type with same name. Next one, elements in an array can be accessed randomly using just the index number. Array memory is predefined, so there is no extra memory loss. Array avoids memory overflow. And finally, 2D arrays can represent the tabular form of data in a very efficient way. Now let us also have a look on some of the disadvantages of using arrays. The first one, the number of elements in an array should be always predefined. So there is no chance that you can add some extra element in the last moment. Array is static in nature, so its size cannot be varied after declaration. What if, consider that you wanted to store 10 student data in one array and you end up having just 7 students. So the remaining 3 is a waste, right? So you are wasting memory there. That's the problem. And insertion and deletion operations in an array is quite difficult as the array stores elements in a continuous form. And finally, allocating excess memory than required may lead to memory wastage. So we will see a brief definition of arrays. The array is a data structure that stores elements of the same data type in a sequential order. Two-dimensional arrays are considered as an array of arrays. Two-dimensional arrays represent the information in the form of rows and columns, which is completely similar to a tabular form of data. Following by the definition and briefing of the two-dimensional arrays, we will understand the need for two-dimensional arrays. So the main advantage of using a two-dimensional array is the elements can be represented in the form of a matrix, that is rows and columns. Using two-dimensional arrays, we can initialize, access and print multiple elements in the matrix form by just running one single code segment. You can see an example right on my screen here. This is an example of marks list. Suppose a class has 3 subjects, namely English, Science and Maths. We have 4 students and we wanted to represent the data in the form of a database. So here, the marks of the 4 students can be represented using two-dimensional arrays. Now, we will see the syntax of a two-dimensional array. So here, the syntax. At first, we need the data type. The data type can be integer, character, float, string, etc. Then we have the name for the two-dimensional array. And later, we can have 2 subscripts which represent 2 dimensions, that is the rows and columns. The first subscript defines the number of rows and the second subscript defines the number of columns. And note that the column number can never be null. And the end, we have a semicolon to terminate the syntax. And here we have some examples of two-dimensional arrays. So in the first example, we have the name of the two-dimensional array and we have 3 rows and 4 columns. And followed by that, we have another example which is of character data type and the name of the array is names and we have 7 rows and 15 columns. Next, we will see how to visualize two-dimensional arrays. We read earlier that two-dimensional arrays are a collection of rows and columns. Let's see an example of two-dimensional array. We will consider an array with 6 rows and 4 columns. As you can see on my screen, we have integer type array and the name of the array is array and we have 6 rows and 4 columns. The product of rows and columns will give us the total number of elements present in a two-dimensional array. In the current example, we have 6 rows and 4 columns and the product is 24. So we must have 24 elements in this array. Next, we will see how to initialize two-dimensional arrays. So there are 2 ways to initialize a two-dimensional array. So in the first method, we declare the elements in the set of curly brackets. This array consists of 3 rows and 3 columns. Note that the index always starts from 0. Here we have 3 rows. It means the row starts with 0 and ends with 2. The same goes for the column. But sometimes this method might be a little confusing. So we have a better method. The advantage of this method is clarity. We can visualize all the elements with better clarity compared to the previous method. So the first 3 elements are 9, 6 and 1. They are present in the first row. And in the second row, we have 144, 70 and 50. They comprise the second row. And finally, the third row in which the elements are 10, 12 and 78. So far, we have learned how to visualize and initialize a two-dimensional array. So we have done it by using the index values, that is the row index and the column index. So the row index value was 3 and the column index value was 3. For accessing an element in the two-dimensional array, we need to pass the name of the two-dimensional array followed by the row index value and the column index value. For example, let us assume that we wanted to access the element 9. For doing so, we will pass the name of the array followed by the row index value and the column index value as shown below. That is int first 0, 0. And an important point here is indexing always starts with 0. We will now start printing the two-dimensional arrays. So to print a two-dimensional array, we will be using 2 nested for loops. So to understand the process of printing the two-dimensional array, let's get back to the practical mode and we will work on a code. So on my screen, you can see an example for two-dimensional array. So here we have declared an array with the name first and we have 3 rows and 3 columns. And inside that, the first row of elements is 9, 6, 1 and the second row of elements is 144, 70 and 50 and the third row of elements is 10, 12 and 78. Followed by that, we have 2 counter variables which are I and j. So we are using the first counter variable I in the outer for loop and the second counter variable j in the second inner for loop. And inside the inner for loop, we have a print statement which is used to print the elements in the array. Now, let us try to execute this code and see the output. So you can see the code got successfully compiled and we have our elements here, which is 961, 144, 70, 50, 10, 12 and 78. Now let us understand the logic. So here we have declared the counter variable as 0 and the condition is I should be less than 3, which is true. So the control will enter into the second inner for loop. Here we have j is equals to 0 and j should be less than 3, which is true. So here the condition or the statement is valid and it will print the first element 9. Followed by that, j will be incremented again. J is now equals to 1 and j is less than 3. So again, we'll print the second element 6. Again, j value will be incremented to 2. So 2 is less than 3. Then we will print the third element, that is 1. Now when you increment the value of j from 2 to 3, the condition will fail because 3 cannot be less than 3. So the control will enter into the outer for loop. Here we have I value is equals to 0, which will be incremented to 1. So 1 is less than 3. Again, the control will enter the inner for loop. Here again, we will check for j is equals to 0, which is true. So we will print the second row of elements, that is 144, 70, 50, in the same way how we printed the first row, right? So j will be equals to 0. So then we'll print the first element. So j will be incremented to 1 and 1 is less than 3. Then we will print the second element, that is 70. And again, j will be incremented to 2 and 2 is less than 3. So we will print the third element, that is 50 in the second row. And again, j will be incremented to 3 now. The compilation of the condition will result in false. So it will exit the second for loop and it will come back to the first outer for loop. Now the value of I will be incremented to 2. So 2 is less than 3. The control will enter into the inner for loop again. Then we will print the third row of elements. That is 10, 12 and 78 in the same way how we printed the first row and the second row. After printing the third row, the condition will fail when j value is incremented to 3 and it will enter the outer for loop. Here the I value will be incremented again from 2 to 3 and the condition fails. Now the overall control will come out of both the for loops and it will terminate here. So that's how we got 9, 6, 144, 70, 50, 10, 12 and 78.
A linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. Typically, a linked list starts with a head node, which goes all the way up to the last node, which is called tail. Next, let's discuss why do we need linked list. A linked list is a linear data structure like arrays, but an array can only offer a fixed size, whereas a linked list can dynamically increase its size. Also, operations like insertion and deletion are much easier in a linked list than in an array. Now, let's try to implement the linked list in the code editor. Let's start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these four nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use add, same arrow formation, and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to N2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail is equals, tail arrow data equals to 7, and tail arrow next is given null. Now let's call up function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. Now let's discuss different types of linked list. The first are singly linked list. Next is the doubly linked list, the circular linked list, and finally we have the circular doubly linked list. Let's discuss each one of these in details. First up, singly linked list. It is a unidirectional linked list. While using the singly linked list, we can only traverse it in one direction, that is from head node to the tail node. Next up, doubly linked list. It is a bidirectional linked list. We can traverse it in both the directions. In this linked list, the node has an additional pointer that points to the previous node. Next up, circular linked list. It is a regular linked list except for its last node points to the head node. Programmer needs to be careful while traversing it, or they might get stuck in an infinite loop. Next up, the circular doubly linked list. It is a combination of doubly linked list and a circular linked list. Its last node points at the head node and the previous pointer of the head node points to the last node. It is also bidirectional linked list so that we can traverse it in both directions. We have now discussed the linked list, why do we need linked lists, and types of linked list. Now let's learn about some operations we can apply on linked list. We can use majorly two operations on linked list. First up, insertion and deletion. We can perform these operations in three different situations. First, at the beginning, at the last, or at a specific position after a node. Next, we will discuss these operations in detail. First up, insertion. We will discuss first insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give the new node's address to the last node's reference pointer. Next up, insertion at a specific position. To do this, we will have to change the reference address of the previous node to the new node's address and the new node's reference pointer to the next node's address. Now, let's discuss deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to the null. Next up, deletion at a specific position. We will change the reference address of the previous node to the next node's address. We have learned a lot about linked list during this session. Now let's discuss some benefits of linked list. First up, a linked list is a dynamic data structure. That is, we can dynamically increase its size. Next, it offers easy insertion and deletion than other linear data structures like arrays and string. Since it can dynamically increase its size, resulting in no memory wastage. Next, it is pretty handy in implementing complex data structures like stacks and queues, etc. Now, let's talk about some disadvantages as well. First up, since the linked list is made up of nodes, it takes extra storage for storing data and reference pointer. Next, the traversal in the linked list is a bit harder than other data structure. Reverse traversing is easy in doubly and circular doubly linked list, but since it uses one extra pointer, it takes extra storage, making it another limitation. So without any further ado, let's get started with introduction to singular linked list. A singular linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. These nodes can be traversed using pointers. It starts from the head node all the way up to tail node. Now let's try to implement the singular linked list in the code editor. Start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these 4 nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use add same arrow formation and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. n1 arrow data is equals to, let's give it 3, n1 arrow next is equals to n2, n2 arrow data is equals to 5, n2 arrow next, 2 arrow next is equals to tail. Now tail arrow data equals to 7 and tail arrow next is given null. Now let's call up function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a We will use while loop to traverse this linked list. We will give it condition if A is not equals to null, then cout is A data and L. Now we will change our cursor from the current node to the next node. To do that, we will use A is equals to A arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. We have now introduced the single linked list. Now let's discuss some of the operations we can apply on a linked list. First up, insertion. We can perform insertion at three different situations, like at the beginning, at the last, or at a specific position after a node. Next up, deletion. Similar to the insertion, we can perform it in three different situations as well. At the beginning, at the last, or at a specific position after a node. Let's talk about them in detail. First up, insertion at the beginning. To execute this, we have to give first node's address to the new node's next pointer. Next up, insertion at the end. To execute this, we have to give new node's address to the last node's next address. Next up, insertion at a specific position. To execute this, we will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now, let's try these operations in a code editor. As you know, a linked list is made up of nodes, so we should start by creating a node. To create a node, we need a class node and we will define its members as public int data and node pointer next. Now we will create a function to insert a new node in front of the list. For this function, as an argument, we will give the reference to the head of the list and integer new data. Now in the definition, we will allocate a node new node equals to now we will put in the data in the new node. We will use arrows to access the data equals to new. Now we will make the next of this new node as head. Now we will move the head to point to the new node. Now we will create another function to insert a node after a specific position. As arguments, we will give it the address to the previous node and the integer new data. We will first check if the given previous node is null. If it is, we will print given node cannot and then we will return the function. Otherwise, we will allocate a new node and then we will enter the new data in that. Now we will make the next of the new node as a next of the previous node. And then we will move the next of the previous nodes as new node. Now we will write a function to insert a node at the end of the list. As an argument, we will give it a node pointer to pointer head and integer new data. We will first allocate a new node we will also create a last node and give it head. Now we will put in the data in the new node Since this new node is going to be the last node, so we will make its next as null. Now, if the linked list is empty, then we'll make the new node as head. To check that, we will use if star head is equals to null. If it is, then we will do star head equals to new node. Else, we will traverse it to the last node. While last next not null, last is equals to last next. Now we will change the next of the last node as new node. Return. Now we will write a function to print this list. While node is not null, cout node arrow data handle and node equals to node. Now we will write the code for the main block. First, we will define a head node. And mark it as null. Now we will start using those functions to make a linked list. First, we will use append function to add 6 in it. Next, let's use another function push and add 7 in it. Now we will try to insert 1 at the beginning. So we will use push again. comma 1. Now let's try to insert 4 at the end. So far the list looks like 1, 7, 6, 4, null. Now let's try to insert 8 after 7. To do that we will use insert after. As argument we will use head next as 7 is present next to the head, comma 8. Now let's try to print this linked list. Cout created linked list print list head. Return 0. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides. Now let's talk about deletion. First up, deletion at the beginning. To execute this, we have to change first node's next address to null. Next up, deletion at the end. To execute this, we have to change the second last node's address to the null. Next up, deletion at the specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in a code editor. We will start by creating a class node. In this class, we will declare the members as public int data and the node pointer next. Now to insert the data in the node, we will use a function push as argument. We will give pointer to pointer node head and integer new data. We will allocate a new node we will give this new node the data as new data and new nodes next as head.
Now we will write a function to delete the node. As argument, we will give a node pointer to pointer, head, and int key. Now we will store head in a temp node. And we will create a node prev as null. If head node itself holds the key to be deleted, we will use if temp is not equals to null and temp data is equals to key. Then head equals to temp next. Now we will free the old node. Else we will search for the key to be deleted. Else while temp is not equals to null and temp data is not key, so prev equals to temp and temp will be iterated to its next. If the key is not present in the linked list, then we will just return the function else we will unlink the node from the linked list. And delete. Now we will write a print list function to print the list. Its argument will be a node pointer node while a node is not null cout less than node data then we will iterate this node using node equals to node next. Now we will move on to the main block. We will start with the empty list node star head equals to null. Now we will add the element to this list. So push ampersand head comma 7. Next push percent head comma 2 push ampersand head comma 5. Next push ampersand head comma 9. Now cout created list print list head now we will use delete node function. Delete 2. We will use argument as ampersand head comma 2. Now we will check the linked list. Of 2. Print list let's try and execute this. As we can see, we have deleted the 2 from the linked list.
A doubly linked list is complex as compared to a singly linked list. In the doubly linked list, the traversal happens in two ways, forward and backward direction, and each node consists of data and address of the previous and next node. As it is clear from the above diagram that the first node's previous is pointing to null, which means no more nodes before it, and its next part is holding the address of its next node, that is the address of second node. Similarly, second node previous is holding the address of the first node and next is holding the address of the third node. Followed by that, the third node's next is pointing to the null because no other node after it, and its previous is holding the address of the second node. This will continue as many nodes are in the doubly linked list. And the elements are located at some random location in the memory. For example, as you can see, if the first element is inserted at the location 2000, then the next element would be located at 2016 and then at the next free location and so on. Moving ahead, let's have a look at the doubly linked list memory representation. Let's consider one example and understand the representation of a doubly linked list. So, consider three elements to be inserted into the list, where each node consists of data part and address part of previous and next node, and it is stored at some address 2000, 2016, and 2022. The address of the first node is stored in the special node called head node. As I discussed before, the first node's previous is pointing to null because there are no nodes before it, and the last node next is pointing to the null because there are no nodes after it. Every node in a linked list is connected in two ways from forward and backward direction with the other through the pointers called previous and next that points to the address of its previous and next node. It is represented by the arrows in this diagram. For example, so let our elements to be inserted be 10, 20 and 30. And the address of the first node is stored in the head node. And the next part of the first node, that is this, is holding the address of the next node, that is 2016. And its previous is pointing to the null. Similarly, the second node is holding the address of the third node, that is 2022. And its previous is holding the address of its first node, that is 2000. Whereas the third node, the previous is holding the address of its previous node, that is 2016, and its next is pointing to the null. And in this way, they are linked together. Up next, we have the syntax of a doubly linked list. A doubly linked list consists of an extra pointer compared to a singly linked list. So, the syntax starts with a struct keyword followed by structure name called node. Then we have the variables declared, that is data, and struct node asterisk next and previous, a pointer variables pointing to an element of a structure node. So with this, let's try to execute a simple doubly linked list program to understand in a better way. So from this program, we are going to create 4 nodes and insert the elements into it. So we have previously discussed this syntax of a doubly linked list. So here we have a previous and next pointer variable. So moving ahead, we'll see that we have a head node and we are creating first, second and third and fourth node. So initially those are null. So they are initialized to null, and for creating we need to allocate the memory for it, right? To create a node, we need to create memory for it. For that we are using malloc function to allocate memory for the node first, second, third and fourth. And once we create memory, we are going to assign the values to it. So here the values are 10, 20, 30 and 40. So these values are assigned in the first data part, in the second data part, third data part and the fourth data part of every node. And once after assigning, we need to link these nodes together. So for that, we have the first next part is assigned to the second. That means it holds of the second element. And its previous is assigned to null because there are no node before it. And the second node's next part is assigned to third and its previous is assigned to first. Similarly, the third next is assigned to fourth and its previous is assigned to the second node. And the last node, that is fourth node's next is null because there are no node after it and its previous is assigned to third. That means it holds the address of a third element. And now the first is assigned to head. That means the address of first node is holding in the head node. And finally displays the first. So this display function we have to display all the element in a doubly linked list. So this will So as you can see, here we got the output. The doubly linked list elements are 10, 20, 30 and 40. Okay, so now let us move on to the operations on a doubly linked list. First, we have insertion operation. Next, deletion operation. And finally, traversal operation. So let's understand them in detail. Under insertion operation, we have insertion at beginning. So basically, we insert the element at the beginning of the element list. Next, insertion at end. That means it inserts the element at the end of the element list. And lastly, insertion after specified node. That means it inserts the element after some specified node. So now, let's run the program and understand these operations practically. So using insertion operation, we are going to execute a simple program. So we have previously discussed that we have two pointer variables, that is previous and next, that is pointing to its previous and the next node. And first let's discuss the insertion at beginning operation. So basically we are going to insert a node at the beginning of a linked list. So for that we are creating a new node and allocating memory for it using malloc function. Once creating the memory, the new data part, the new node's data part is holding the new data. And the next is pointing to the head. And its previous is pointing to the null because there are no nodes after it. So if head is not equal to null, that means head's previous is equal to new. And now new is assigned to the head. So it's simple. Now the head is holding the address of a new node. Next, coming to the insertion at end. So here again, we are creating a new node, allocating memory for it, and that new data is holding the new data, and its next is pointing to null because there are no more nodes after it. And we are creating a temporary variable where true hold the address of a head. So now if the head is equal to null, that means new previous is pointing to the null and new is assigned to the head and return. While the temp next, if it is not equal to null, then the temp next is assigned to the temp variable, and now the new is assigned to the temp next, and temp is assigned to the new previous. So now the last node is inserted. Now coming to the insertion after node, that means inserting in between of two nodes. So if previous node is equal to null, that means the given previous node cannot be null. For that, we are creating again a new node and allocating memory for it using malloc function, and its new data is holding a new node's data part is holding the new data, and the new node next part is assigned to the previous node's next, and we are just changing the addresses. So now here previous node next is pointing to the new, and the previous node is now assigned to the new previous. So if new next is not equal to null, that means new next previous is equal to new. So coming to the display here, while node is not equal to null, it will print all the node data till it finds the null. And here in the main function, we are creating a head which is initialized to null initially, and when the control comes to the insertion at end, it will print a value 4. And next, when it encounters the insertion at beginning function, that means it will insert 2 in front of the element 4. And again, insertion at beginning. So it insert the element 1 in front of element 2. And similarly, insertion at end. That means it will print element 5 after the element 4. And insertion after node head next. That means it will insert the element after the element 2. So now let's try to execute and run the program. So as you can see, the elements are listed in a proper way. That means we have the elements 1, 2, 3 4, and 5. Followed by that, we have deletion operation to delete from the beginning, delete from the end, and delete after a specific node. So now let's run a program. So now we are going to perform the deletion operation. So for that, we have a function called deletion node. So basically we are going to delete a node from a list. So first, it checks the condition if head is equal to null or node delete is equal to null. That means a node to be deleted is also equal to null, then it will return. That means the deletion is not possible. Next, it checks the next condition if head is equal to node delete. That means if a node to be deleted is our first node, then head is equal to head nodes next. That means the head node next is assigned to the head. Next condition, if node delete next is not equal to null, that means if it is not the last node, that means point the previous next node to the node delete previous. And finally, if node delete previous is not equal to null, that means if the node to be deleted is not the first node, then point the next previous to the delete node delete next. And finally, we are going to free up the memory space for that node. And coming to the main function, where we have print function, after deleting an element, it's gonna delete the node. So here after the head, next 1, 2, 3, 4th. So after the 4th node, it's gonna delete the 5th element. That is, it will delete the last element 5. So let's check the output. So as you can see, after deleting an element, so our previously inserted elements were 1, 2, 3, 4, and 5. And after deleting, now the element 5th is deleted. Finally, we have traversal operation. In this operation, we visit each and every node at least once, maybe to display all the data elements or to perform operations on it. So let's understand it practically. So here we are going to perform a traversal operation. That means it actually visits each and every node at least once and display them. So here, using a display function, we are going to display all the elements that are present in a linked list. So now let's try to execute and run it. So as you can see, first the inserted elements were 1, 2, 3, 4, and 5. And after deleting an element, now the elements are 1, 2, 3, and 4. That means the 5th element got deleted. And now the final list of elements are 1, 2, 3, and 4. I hope you got a clear understanding of how to perform insertion, deletion, and traversal operations in Doubly linked list.
Now, let's begin by understanding what a circular singly linked list is in C. In a circular linked list, we can perform a circular singly linked list and circular doubly linked list. So this session is on a circular singly linked list. In the circular singly linked list, there is no null in any of the nodes. Instead, the last node's next pointer holds the address of the first node. So basically, there is only one pointer variable in the circular linked list. And the traversal of a circular linked list is until we reach the same node we started in a list. Moving ahead, let's have a look at the circular singly linked list memory representation. So first, let's consider 4 elements to be inserted into the list. And for that, we have 4 nodes, where each node consists of data part and address part stored at some address 2000, 2016, 2022, and 3000. In the singly linked list, the last node points to null. But when we compare a circular linked list with singly linked list, we don't find a null. Which means, in a circular linked list, the last node's next pointer holds the address of the first node. In other words, we can say that the tail node's address is pointing towards the head node of the linked list. And as I discussed before, every node in a linked list is connected with the other through a pointer that points to the address of the next node. and that is represented by the arrows in this diagram. For example, so let our elements to be inserted be 10, 20, 30 and 40. As you all can see, the last node next is holding the address of the first node, that is 2000. And the next part of the first node is holding the address of its next node, that is 2016. Similarly, the second node is holding the address of its third node, that is 2022. And the third node is holding the address of its next node, that is 3000. And the last node is holding the address of the first node. And in this way, they are linked together. Up next, we have a syntax of a circular singly linked list. The syntax of a circular singly linked list is similar to that of a singly linked list. So, we have a struct keyword followed by a structure name called node. Then, we have a variables declaration, that is data and struct node asterisk next, a pointer variable pointing to an element of a structure node. So with this, let's try to execute a simple circular singly linked list program to understand in a better way. So in this program, we have a pointer variable called next, and inside the main function, we are creating nodes, and they are first, second, third and fourth. So for every node, we need to allocate memory for it. So using malloc function, we are creating memory, or we are allocating memory for it. And once allocating memory, we are inserting values into it, and the elements are 10, 20, 30 and 40. And once inserting value, we need to link each and every node. So for that, first next is holding the address of second node, second next is holding the address of third node, and third next is holding the address of fourth node, and the last node, that is fourth node next, is holding the address of its first node, and last is equal to fourth. And display function will display all the elements in a circular singly linked list. So it first checks the condition. If the last node is equal to null, then the list is empty. Pointer is equal to last node's next, do. So it checks the condition. It prints the values, that is pointer's data. It prints the data of every node and then checks the condition while pointer not equal to last node's next. So now let's try to execute. And here we got the output. The elements are 10, 20, 30, 40 inserted into a circular singly linked list. Okay, so now let us move on to the operations on a circular singly linked list. First, we have the insertion operation. Next, the deletion operation. And finally, the traversal operation. Let's understand them in detail. Under insertion operation, we have insertion at beginning. So basically, we insert the elements at the beginning of the element list. Next, insertion at the end. That means it inserts the element at the end of the element list. And lastly, insertion after a specified node. That means it inserts the element after some specified node. Now let's run the program and understand these insertion operations practically. So in this program, we are going to perform insertion operation. So first let's start with insert to empty list. So we are going to insert a new node into an empty list. So if head is not equal to null, then return head. Create a new node and allocate memory for it. And once creating memory, assign a data. And now the new node is equal to head. And head next, that means creating a link to itself. Head next is equal to head and return head. And next we are going to perform insertion at beginning. So insert a new node at the beginning of a linked list. So if head is equal to null, then return to insert to empty list function. Create a new node and allocate memory for it. And then assign a value for a new node. So new data is equal to data. Now new next is equal to head next. So the new is the head node, return head. Next, we are inserting an element at the end of a linked list. So for that, it checks the condition if last is equal to null, return to insert to empty list function and create a new node, allocate memory and assign a data, and now link the address. So new next is equal to last next. Now the new node is the last next and return last. Next we have insertion after node. So it checks the condition last is equal to null, then return null. Else we are creating here the new and a pointer variable. Pointer is equal to last next. So do if pointer data is equal to element, that means if we find the element, then allocate memory for the new node and assign a data, and now new next is assigned to pointer next, and now the pointer is assigned to the pointers next, and if pointer is equal to last, then assign new to last and return last. Next, pointer is equal to pointers next. So while pointer not equal to last next, the given node is not present in the list and return last. Next we have display function where it displays all the linked list elements. So for that it checks the condition if head is equal to null, then the list is empty. Else it will print all the elements of a node. So now coming to the main function, here we have inserting values. There are 20, 25, 10, 15. So first insert to empty list. So we are inserting the 20 to the empty list, that is the first element is 20, and then coming to insert at end, after 20 it will print 25, and insert at beginning. So before 20 and 25 it will insert element 10, and insert after node, that means after 10 it will print 15. So now let's execute and see the output. As you all can see, it is printed in a order 10, 15, 20 and 25. Followed by that, we have a deletion operation to delete from the beginning, delete from the end and delete after a specific node. So now let's run a program. So in this program, we are going to perform a deletion operation. So we are basically deleting a node. So for that we have a delete node function. It first checks the condition if last is equal to null. That means if the linked list contain no elements, then it return. Else it will check whether the list contain a single element. So if last data is equal to key node and last next is equal to last, then free the last and assign last is equal to null and return. Next, creating a temp variable is equal to last and delete node. So here it will delete a last node. So for that, if last data is equal to key node and while temp next is not equal to last, and assign temp next to temp. So here the last next is assigned to temp next and free the last, and temp next is assigned to last. Then we are traversing to the node, or we are finding the node to be deleted. So for that we have while temp next is not equal to last and temp next data is not equal to key node, then assign temp next to temp, and if the temp next data is equal to key node, that means if you find the node to be deleted, then assign the temp next to delete node and delete node next to temp next and free up the delete node space. And then coming to the main function, it prints after deletion the linked list elements. So we are going to delete the element 15 from the list and it displays the element. So now let's execute it. So as you can see here, the linked list elements were 10, 15, 20 and 25. So after deletion, that means we deleted the element 15. So after deletion, the linked list elements are 10, 20 and 25. And finally, we have traversal operation. In this operation, we visit each and every node at least once, maybe to display all the data elements or to perform operations on it. So let's understand it practically. So in this program, the display function works as a traversal. So it traverses the every node in a linked list. So basically, it first checks the condition. If head is equal to none, then the list is empty. It prints the list is empty if it does not find any node in a linked list. Then it returns. Now assign the head next to pointer so that it prints the data of every node and checks the condition while pointer not equal to head next. Coming to the main function, here we have it prints the elements of a linked list. That means after the insertion and deletion operations, it will print all the elements present in a linked list. So now let's try to execute it. So here linked list elements are 10, 15, 20 and 25. So after deletion, the linked list elements were 10, 20 and 25. Then it displayed the elements after deletion and insertion. The elements are 10, 20 and 25. So the final linked list elements are 10, 20 and 25.
So at first, what exactly is an array? So an array is a linear data structure that stores homogeneous data elements in a continuous form. So homogeneous in the sense, you will be able to store only one single data type of elements in an array. For example, consider that you have declared an array and you wanted to store some elements in the array. So you can declare a data type first, after that the name of the array, and if you declared that the array should store integer data type, then you can only store integer elements in that particular data type. You cannot store any other data type like float or character. That is the meaning of this particular definition. And it stores the elements in a continuous order, that is in the adjacent format, as you can see in the example here, 10, 20, 30, 40, and which are located in the adjacent locations, that is 0, 1, 2, and 3. Now let us understand what exactly is a linked list. So similar to array, even a linked list is a linear data structure. But the only difference is it is a dynamic data structure. Here, you can increase or decrease the size of the linked list in runtime. The only difference is here the memory locations are not adjacent to each other, but they are taken from the memory heap. So there is a huge memory chunk. Out of that, the linked list will borrow some of the memory locations, and one after the other, the memory nodes will be interconnected using pointers. So that was the difference between array and linked list. And similar to arrays, even the linked list store homogeneous type of elements. That is, if you declare a linked list of float data type, then you can only store float data type in it. You cannot store any other different data type like character or string. Now followed by that, let us understand the types of arrays. So basically we have three different types of arrays. Those are the one-dimensional arrays, and inside multi-dimensional arrays we find two more types. Those are the two-dimensional arrays and three-dimensional arrays. Now one-dimensional arrays will be having only one subscript, that is, they'll be having only one single row. Whereas in the two-dimensional arrays we will be having two subscripts, that is, it will be having rows and columns. And in the three-dimensional arrays it will be having three subscripts, that is, the row, column and the block address. Now followed by the types of arrays, we will understand the types of linked lists. So similar to arrays, even linked lists are divided into three types. They are singly linked list, doubly linked list and circular linked list. The difference between them is a singly linked list will have two parts, that is the node address and node element. In this particular segment, the element will be stored, and in this particular second segment, the address that points to the next node will be saved. And similarly in the circular linked list, the only difference between the singly linked list and the circular linked list is at the end of the singly linked list, you can see a null pointer which indicates the end of the linked list. But in circular linked list, the address will not be null. Instead, it will point back to the head node. That is what which makes it as a circular typed singly linked list or a circular linked list. When it comes to the third type, that is the doubly linked list, we can see there are two address locations. The first starting node will have null as its first address location, then we'll store the element, and the second address location will point to the next node. And you can see in the second node will have element, and the first address location will point to the previous node, and the second address location will point to the next node. And at the end, the second address location will be pointed as null, which indicates as the end of the linked list. Now that we know the types of linked list and arrays, we will look into the fundamental differences between arrays and linked lists. So the first fundamental differences between the arrays and linked list is the array element can be accessed randomly using just the index values. But whereas random access is not possible in linked list. If you want to access any element in linked list, you need to perform the traverse operation sequentially. The second difference between the both is array is static, which means memory size is fixed, which cannot be changed in runtime. But whereas in the linked list, the memory is dynamic, which means you can either shrink or expand the memory in runtime according to your requirements. Followed by that, the next difference is each element in array is independent in nature. That is, you can access any element just by giving the index location. Whereas in linked list, the elements are interdependent on each other. Whenever you want to access a specific element, you need to go through the other elements or traverse through the other elements. Next one is the array takes more time in operations like insertion and deletion, whereas linked list takes less time to perform the operations of insertion and deletion. Followed by that, the next difference is accessing any element is faster in array as random access is possible, and the array data structure just by using its index values. But whereas accessing an element in linked list is slow because we know that we need to traverse through all the node elements to access a particular element. Now the next difference is, in case of an array, memory allocation is done in compile time. Whereas in linked list, the memory allocation is done during the runtime. Memory utilization is inefficient in an array as it is allocated as in static and it is allocated during the compile time. In case of linked list, the memory utilization is very efficient as the memory is allocated during the run.
What is a stack? So basically, stack is a linear data structure just like arrays and linked lists. The only difference is that it follows a specific order when an operation is implemented on it. So what is the specific order that it follows? That is LIFO, last in first out, or FILO, first in last out. In the next parts, we will understand this order in a much better way. All operations can be done only at the one end of the stack, that is on the top. Now we will discuss much about that in the operations part of the stack. Now let us understand the first fundamental, that is the representation of stack. That is, how do you represent a stack normally? So a stack can be represented using two different methods, that is using an array or using a linked list. So in an array we will be using the continuous memory. And in stack, we will be using a non-continuous memory, and the stack will behave like a dynamic stack or a dynamic data structure. Now the first method, that is the array method. So in this method, an array is used to represent the stack. As you can see in the image below, we have a stack. So the name of the stack is stack itself, and you can see two more things here, that is top is equals to 2 and max is 4. So the max is the value of the array or the length of the array, the maximum length of the array, and top is the position where the last element of the stack is present. Here in this case, 56 is the last element in the stack and top is inclined, or it is addressing to that particular address, that is 2. And now let us discuss about the linked list representation of stack. So in this method, a dynamic data structure, that is a linked list, is used to represent the stack. This representation leads to a dynamic stack. It does not need to define the maximum number of elements present in the stack. Remember, in arrays, we had to define the max value. In the previous example, we had the max value as 5, but in here, you need not to assign the max value as the stack itself is dynamic. The pointers links are used to store the address of the upcoming nodes, and the variable used in this method is top. So the top is holding the address of the topmost element in the linked list representing the stack. Now moving ahead, we shall understand the basic operations on stack. Now here we will understand the previously discussed definition, that is push, pull, etc. in a much better way. So the basic operations on a stack are push, pop or pull, and peek. Now let us discuss each one of them in a detailed way. The first one is push operation. So the push operation is the mechanism of inserting a new element into the stack. As you can see, we are trying to insert the elements from the top. So the push operation basically involves the following steps. Check if the stack is either full or not. So basically, whenever you're trying to insert an element into the stack, you need to make sure that the stack is empty or it has some space. If it is full, you cannot insert an element into the stack. Step 2. If the stack is full, produce an error and exit. That's what I was talking about. Now the step 3. If the stack is not full, increment the top by 1. That is, when you're inserting an element, then you need to update the top value. For example, in the previous slide, when we had the array representation of a stack, we had the top value as 2. So if you try to include an element into the stack, then you need to update the top value from 2 to 3. That is incremented by 1. Now the fourth step, add data elements to the stack where the top is pointing. And finally, success. The push operation has been successful. So this is how you insert or push an element into the stack. Now followed by push operation, we have pop or pull. So the pop operation is a mechanism of eliminating or deleting or removing one data element from the existing stack. So we shall understand the pop operation in a much more detailed way. The operation involves checking the stack is empty or not. If in case the stack is not empty, then you can carry forward the pop operation. But in case if the stack is empty, then you have to provide an exit status and exit the control and leave the stack. So if the stack is not empty, approach the data element at the top, that is at the top position. For example, in the previous array example, remember, right, we had the top position pointing towards 2. So you need to take the control to the top position and pick out the element and pop it. And finally, decrease the top by 1. So when you eliminate the top element, then the top value from 2 will be decremented to 1. So this is how the pop operation is carried over on a stack. Next one is the peek operation. The peek operation involves returning the topmost data element from the stack without moving it. So here you can see the top is pointing to the element number 4 and you're peeking the element number 4 and you're not removing it from the stack. You're just returning the topmost data element. You're passing the value of the top element. So to understand the push, pop and peek operations on stack in a much more better way, let's carry out a practical example. Now we are on the practical mode and here you can see on my screen we have the code example for the stack. Now first we'll be checking if the stack is empty as per the steps mentioned in the previous discussion. We will check if the stack is empty or not. If it is empty, then we will return, else we will continue. And again another step, we also check if the stack is full. If the stack is full, we will exit, else we will continue with the operation, whatever it is, peek, pop or push. And here we have an example for the peek operation that we discussed previously, and followed by that we have a pop operation. We are trying to exclude an element from the stack, and another one we have the push operation where we'll be trying to push the elements into the stack. So these are the three functions for push, pop and peek. Now we'll try to push in the elements and also pop and try to involve some functions on it or run some operations on the stack. Now let's run this code and see the output. So you can see that the code has successfully executed and we have the statements here. The first one says the stack is not full, that is false, and stack is empty, that is true, right? And after that you can see that the elements which we tried to push into the stack, that is 11, 76, 71, 15 and 66 are been pushed into the stack. And if you clearly observe it, we have the element 11 in the bottom, 76 upon that, 71 upon that, and 15, and last 66. So the order is first in, last out. That is, the first element was pushed first, and when you are trying to eliminate the elements from the stack, then you will first pick out 66, followed by that you will pick out 15, followed by that you will pick out 71, and so on. So this is the rule what stack follows. Now I hope I made myself clear with the example. Now we shall continue with the applications of stack. So these are the few applications of stack. The first one is expression conversion. So you can see we have the infix notation, prefix notation, and postfix notation. So the infix notation is no rocket science. There is only one thing here to learn, that is we have two operands A and B, and we have one operator, that is the addition operator, in between those two operands. And when you use the prefix notation, you will have the operator located at the first place, then you will have the operands followed by it. And in the postfix one, you will have the operands first, and followed by the operands you will have the operator. So basically all the infix, prefix, and postfix notations give out the same results, but the only difference is the representation of those operands and operators. Now let us understand this in a much more detailed way. So conversion of expression from one form to another form is the main application of stack. So we have the first one, that is infix to prefix and infix to postfix. Now let us see an example. Here you have 1 plus 2 star 3 plus 4. So this is the normal infix notation. And when you try to present the same expression in the form of prefix notation, so this will be the result, and this is the result for postfix. The next one, prefix to postfix and prefix to infix. And this is the way you write the prefix notation, and if you want to convert that to infix, this is how you can write it. And this happens to be the result of postfix notation. And finally, postfix to prefix, postfix to infix, and these are the results. Now followed by expression evaluation, the next important application of stack is checking parentheses. And you can see if the parenthesis is set properly, the expression gets evaluated. If not, it will not be evaluated. Now the last one, memory management and function call. The very useful thing of using a stack is the memory will not be allocated to your stack elements unless the function is called. Here you can see it is the main function, and these are the elements that you wanted to declare into your stack. And unless you make a function call, the elements will not be declared their memory, or the elements will not get the memory allocated for them. Now another good application of stack is the backtracking problem, or the n-queen problem. The n-queen problem is an example of backtracking problem. The n-queen solution to this problem is to position the queen in such a way that the opponent queen cannot attack your queen. Now another example is string reversal. You can see on my screen we have a string that is A, B, C, D, and E. Now using stacks you can reverse this. Right? So you're basically eliminating an element and relocating it to the first place. And finally, after reversing your string, this will be your result, A, B, C, D, and E. Followed by that we have conversion evaluation. So stack is used to evaluating the expression as shown in the example. Since parenthesis has the highest precedence, 5 plus 4 gets evaluated first, and it will result in 9. Then multiplication and division have the same precedence. Now the associativity comes into picture. So the associativity is always from left to right. So first 4 into 9 will be executed, which will result in 36, and then 32 divided by 4, which will give us 8. Now we have 36 minus 8, which will give us an answer that is 26. Now the last application is the Tower of Hanoi. So the Tower of Hanoi is a mathematical puzzle consisting of 3 rods and n discs. This puzzle consists of some rules. The first rule states that one disc can move only at a time.
The second rule is that the disk can only be moved when it is at the uppermost position on the stack. The third one, no disk is allowed to place on the top of the smaller disk. So this is how the Tower of Hanoi works. So a stack is a linear data structure that follows FIFO or first in, first out principle. All the operations on the stack are done only from one end, that is the top. So you can see this image here, and this particular image of books can be considered as stack. And you can see that the addition or elimination of elements, that is books in this particular case, is happening only through the top section. Now we will understand what are the basic operations that can be performed on a stack. So the basic operations that can be performed on a stack are push, pop, and peek. So this particular image on the right side will help you understand what exactly is push, pop, and peek. As we discussed, the elements will be added into the stack from the top. So when you add an element from the outside into the stack, it will be pushed from the top. That is the push operation. And if you want to eliminate an element from the stack, it will be eliminated from the top. That is the pop operation. Apart from these two, that is push and pop, we have another operation that is called as peek. The main intention of peek is just to see the element which is on the topmost part of the stack. It will just retrieve the element from the top. It will not pop it, or it will not push any other element onto the top. It will just copy and it will just print what is present on the top. So these are the main operations, that is push, pop, and peek. Now let us see how to implement this stack using array. So implementation of stack data structure can be done in two ways, that is array and linked list. Now in this particular session, we will learn how to implement stack using array data structure. Now without further ado, let's get started with the implementation of stack. So we will be performing push operation, that is inserting a new element into the stack. Now followed by that, we will be performing the pop operation onto the stack, that is eliminating or deleting an element from the top position of the stack. And followed by that, the last operation, that is the peek operation, where we will be just retrieving the topmost element from the stack without removing that element from the stack or without adding any new element to the stack. Now that we have a detailed understanding of what are the basic operations that can be applied onto the stack, let's get started with the practical implementation. Now you can see that on my screen we have the basic fundamental operations onto stack, that is the push and pop. Now without further ado, let's get started with running this code. Don't worry about the code. This particular code will be present in the description box below, or if you need it, you can always write down to us in the comment section below and we will have it sent to your mail ID so that you can have a better understanding of the code and try to execute the code in your local system. Now let's run the code and see the output. As you can see, the code got successfully executed and the topmost element is A and the topmost element is B after the element is being popped away, and it says that the element B was popped out, and after that the topmost element was A, and after that the element A was also popped out, and now the top is pointing to -1, which means to say that the stack is empty. So with that, we have come to an end of this tutorial on stack implementation using array data structure. So first up, what exactly is a linked list? So linked list is a dynamic data structure. It allocates memory dynamically. The nodes are maintained in a non-continuous memory. That is, in linked list, we have nodes. So each and every node is connected via a pointer, which points to the address of the next node. Each node contains next pointer, that is the next pointer's address, which keeps the reference to the next node. And it also has another section which stores the data. The topmost node always contains null in its address. And this is how a linked list looks like. So this is the top, which is the beginning position of the linked list, and this is the address of the first location, and this is the next node, this is the following node, then this is the last node, and this points back to the head node. So this is how you can implement a stack like data structure using linked list. You can see that we can perform stack like operation, that is the elements are located one above the other and the top is pointing to the head node. Now let us go through the implementation of stack using linked list. First, we will go through traversing of stack using linked list. So displaying each node of the linked list representing stack is termed as traversing. Copy the head pointer to the temporary pointer and then move temporary node through all the nodes and display values of each node. So you can see the animation here will explain you how the traversal goes through the linked list in real time. Now another linked list implementation of stack is the push operation. So adding a new node to the top of the stack is termed as push operation. Generally in stack we have three operations, that is push, pop and peek. So one of the operation is push, where you add an element into the stack. In the same way, using linked list you can add a new node to the stack and point it as the top of the stack or the first element which represents the top in terms of stack. Now create a node first and allocate a new memory to it. If the list is empty and node consists of data and null is the address, it will be inserted as the first node. If there is some node already existing, then add a new node at the beginning to avoid violations. So the following animation will help you understand how we add a new element or the top element to the stack using linked lists. Now followed by the push operation, we have the pop operation. So now let us go through the pop operation. Removing a node from the top of the stack is termed as pop operation. In the same way, we will be eliminating the first node from the linked list, which is termed as top. Underflow condition may occur when you try to remove the node if the stack is already empty. In stack, node can be removed from one end only. Therefore, the value stored in the head pointer must be deleted and the node must be freed. Followed by the pop operation, we have the peek operation. Retrieving the topmost node of the linked list representing stack without removing the linked list node from the top of the stack is termed as peek operation. Generally, when you're using a stack data structure, just retrieving the value of the top node is called as peek operation. You're not going to eliminate or you're not going to add a new element to the top. You're just going to copy the element or you're just going to retrieve the element which is pointed as top. This operation is called as peek. Now, in the linked list, you can also perform this operation of peek. Now, with the theory discussed, let us execute a practical program based on stack implementation using linked list. Now, on my screen, you can see a code example using which we will implement stack using a linked list. Now, here we have the pop operation, push operation, and top, and then the main function. Don't worry about the code. This particular code snippet will be attached in the description box below, or you can also request us and we will have it sent to your mail ID and you can understand the code and try executing in your local system. Now without further ado, let's directly run the code. So there you go. The code got successfully compiled and we have tried to add some elements into the stack, that is A, B, C. And C is being the topmost element of the stack, and that element has got popped, and followed by that the element on the top currently after C being popped out is B, and the node element B got popped again, and the only element which was present in the stack is A, and that element is also popped out after performing the pop operation, and now currently the stack is empty. You can see that we have tried to push the elements A, B, C, and also we tried to pop the elements A, B, C.
You know that all of us depend on messaging applications like WhatsApp, Facebook Messenger, Instagram chats to communicate with our friends and family members. And while using them, you must have observed that the person you are trying to communicate with receives messages in the same order as you have sent them. Now the question that arises here is, how is this happening? How are these applications maintaining the order of these text messages? And the solution to these questions bring us to queue. Basically, in these applications, a queue is maintained for each user, containing the messages to be delivered to the user. When the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. This example clearly illustrates the importance of data structures. So let's dive further and understand the structure of the queue in depth. But before doing that, let's look at a real-life example of queues to understand it more clearly. The most common and relevant example of a queue is a movie ticket counter. In the movie ticket counter, you must have observed that both of its ends remain open. Also, these ends are fixed with the help of barricades, and that is why no one can enter in between these ticket lines. Additionally, the person who enters first receives a ticket first, and the person who enters last will obviously get served at last. Queues in data structure resembles all these properties of a movie ticket counter, which makes them better at creating virtual first-come, first-served systems. Basically, they are defined as a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. The end at which insertion takes place is called rear, and the end at which deletion takes place is known as front. Furthermore, there are two approaches to consider the structure of the queue, and both of them depend on the approach of the programmer. That means, being a programmer, if you consider the left end as front, then your rear node will be at right end. Otherwise, if you consider the left end as rear, then the right end will be your queue's front node. Unlike arrays and linked lists, elements in the queue cannot be operated from their respective locations. Here, they can only be operated from the front or rear position. Moving on, let's discuss the operations in queue data structures one by one. The first operation is enqueue. It is used to store the elements in the queue. Next up is dequeue. This operation is used for removing them. Further, we have isFull and isNull operations. IsFull function scrutinizes if the queue is full or not, and the isNull operation evaluates if the queue is empty. We also have a peek operation that helps you get the element from the front of the queue without removing it. Let's now understand how these operations work with the help of the following examples. Here we will look at enqueue5, enqueue1, enqueue-2, then isFull, then dequeue, peek, and isNull. But before explaining these operations, it's essential that we initialize the queue data structure by assigning some random size to it. For example, int queue of 3. By this declaration, we are assigning only 3 spaces for insertion in queue. Also, at this phase, there is no element in the queue as it's empty. So both the front node and rear node will point to the same location with null memory space in the storage system. Let's consider that null index to be -1 for ease of our convention. Now the first operation on our list is enqueue of 5. As we discussed previously, enqueue operation is nothing but the insertion of data into a queue data structure. It begins with checking if the queue is full or not. If the queue is full, then the previously assigned memory is completely filled with data elements. So insertion would not be possible. This is also known as overflow error in terms of programming. But as our queue is empty, so the insertion can be performed here. For that, we have to increment the rear pointer to index 0 from index -1. And once we do that, the data element 5 will be added to the queue. Also for front insertion, both front and rear will point to the same location as there is only one element present in this queue. Let's insert 2 more elements into this queue with the operations enqueue1 and enqueue-2. For that, we have to increment the rear pointer to the next index, which will be 1. Now, as the pointer is incremented, so the data will be entered into this position. Next up is enqueue-2. Again, we have to follow the same process of incrementing the rear pointer. We will increment the rear pointer to point towards the next index, that is index 2, and hence the data element with value -2 will be entered here. The next operation on our list is isFull. In this operation, if the rear pointer points to the max size, then the queue is considered to be full as there is no space left for insertion. In our case, the max size of our queue is 12 bytes. Additionally, we are considering to enter only 3 integer elements. And one integer data element takes 4 bytes of the memory space. That means 3 integer elements will take 12 bytes. Hence, this function will prompt queue is full on the screen. Now we will discuss the dequeue operation. If we want to access data from a queue, we have to perform 2 subtasks. The first one is access the data where the front is pointing, and another is to remove the data after access. And this complete process is called as dequeue operation. The first step of this operation is to check if the queue is empty. If the queue is empty, then there is no element available for deletion. This is a case of underflow error. But as our queue is not empty, we can proceed with the next steps. We will be accessing data from the front node, and later we will be incrementing the front pointer in order to remove the link to the previous node so that the data gets removed. Now, front will point to the index 1. Thus, the data value 5 will be removed from the queue and will also be prompted on the screen. Therefore, this function comes with an integer return type. Next up is peek operation. In this operation, element at the front node will be accessed without deleting it. The algorithm for this operation begins with checking if the queue is empty or not. If the queue is not empty, then data at the front node will be accessed with temporary variable and printed on the screen. Advancing further, let's perform 2 more dequeue operations here. First is dequeue of 1 and another one is dequeue of -2. The data at a front node will be accessed primarily, and the front pointer will be incremented to point to the next data element. When we do the pointer incrementation, the link to the previous node gets removed, which results in data deletion. Similarly, we will perform a dequeue of -2 operation here. Now, the front will be pointed to null memory space as there is no element left in our queue, and the data -2 will be removed. The last operation on our list is empty. This function checks if the queue is empty or not. In the previous procedure, we mentioned that if the front points to the null memory space, then the queue is empty. And in our case, the front is already pointing to -1. So the output of this function will be queue is empty. This is all about operations in the queue. I hope that you all are clear with these operations. Next, we will discuss different types of queues and their structures at a glance. Basically, there are 4 types of queues: linear queue, circular queue, priority queue, and double-ended queue. The structure which we have discussed till this time is that of a linear queue, so now we will move on to circular queue. The circular queue is almost similar to the linear queue, except that the last node of this queue is connected to the first. It is also known as ring buffer as all the ends are connected to another end. Additionally, this circular queue is a better version of the linear queue as it removes the drawback of insertion in the linear queue. The empty space available in a circular queue can be filled with the new element by simply incrementing the value of the rare position. We will learn about this in detail in our further sessions. A priority queue is another special type of queue data structure in which each element has some priority assigned with it. Based on the priority of each element, the elements are arranged in a priority queue. If the elements occur with the same priority, then they are served according to the first in, first out principle. In the priority queue, the insertion occurs based on the arrival, while the deletion occurs based on the priority. The above figure shows that the highest priority element comes first, and the elements of the same priority are arranged based on the first in, first out structure. The last type of queue is dequeue. Dequeue is a linear data structure in which the insertion and deletion operations are performed from both the ends. We can say that dequeue is a generalized version of the queue. Dequeue can be used as stack as well as queue as it allows the insertion and deletion operations on both the ends. If the insertion takes place at one end and deletion at another, then that dequeue is known as a linear queue. And if both addition and deletion are performed at a single end, then that dequeue is called stack. Advancing further, let's discuss some applications of queues to gauge an insight into the importance of queues. The queue data structure is used in computers, printers, and applications to utilize the benefits of the first come, first served technique. In computers, whenever you work on documents or PPTs, you must have observed that whichever key you press on the keyboard appears in the exact same order on the screen. But when your processor is too busy with other tasks, you might notice that the keys you press appear on the screen with some delay after you press them. Basically, those keys are stored in queue, and when the processor becomes free, it processes in the order the keys are pressed. That means the key pressed first will be written in a Word document first. So this is how computers use a queue to eliminate deadlocks when multiple processes are in a ready state. Next up is printers. A queue data structure is used in printers to maintain the order of pages while printing. That means the pages are stored in a queue in the order that you want to print them, and once the page is removed from an ordered queue, it gets printed. Another most common application of queue data structure is their usage in web or mobile apps. Applications like Domino's, Swiggy uses a queue for maintaining food order status. If you place an order from an online portal, your order ID enters the queue, and once the previous orders before your order ID gets catered, then your order will be catered as well. From these examples, we can clearly say that queues are used whenever there is a need for an FCFS strategy in software development. So whenever you work on projects that need a first-come, first-serve approach, then remember that you have to implement a queue data structure to complete it successfully. Finally, let's have a look at some key takeaways that we discussed in this session. We started this session by examining the structure of the queue. We learned that the queue is a linear data structure. After that, we talked about different operations of queues in which we learned enqueue and dequeue are responsible for data manipulation in a queue. Later, we discussed different types of queues as well. Finally, we discovered some applications of queues and how they fulfill the need of FCFS systems. We have also made it clear that queues can handle multiple data types as well. We will be discussing about stack versus queue. Primarily, we will discuss the definitions of both these data structures first. The stack is a linear data structure similar to arrays and linked lists, restricting the random access of elements. In the case of arrays or linked lists, you can access elements by either traversal or random indexing, which is reframed in stack data structure. You can understand a stack by visualizing it as a container of elements in which elements can only be placed on top of each other and removed from that same direction only. Stack as a data structure in computer science is not very different from stack as a way of organizing objects in the real world. So stack can be thought as the way you arrange books stacked on top of each other. These books can only be placed upon each other from the top end. Furthermore, to remove any particular book, you will first have to remove books stacked over it. This scenario accurately depicts sequential book access, equivalent to the stack data structure in computer science. The queue in data structure is also a linear data structure like a stack, having some restrictions on insertion and deletion. In the case of queue, insertion is performed from one end and the removal is performed from another or opposite end. The queue in data structure can be understood using the real-life example of a food court line. In any food court line or a movie ticket counter line, the customer who enters first always gets served at first, and the customer who enters last will absolutely get served at last. Furthermore, both the ends of these queues remain open, performing different operations. The rear end of the food court queue performs the insertion of a customer, whereas the front end performs the removal of the customer after providing him with the service that he desires. Both the stack and queue data structures follow the different operational principles to execute data manipulation operations. The stack data structure follows last in, first out, or first in, last out principles to execute its operations. In simpler words, the stack data structure removes the last inserted element at first and the first inserted element at last. Let's understand the principles mentioned above with the help of an example. As you can see in this example, 3 is the last inserted element, and if we start removing elements from this stack, 3 should get removed at first, and 7 should get removed at last. Unlike stack, the queue data structure follows FIFO, which is the first in, first out principle, to execute its operations. According to this principle, the element which gets inserted in a list at first gets removed at first as well. For example, in this queue, 6 is the element which is inserted first. So, while performing the deletion, it should also get removed before all the other elements inside the queue. Moving forward, let's discuss different data manipulation operations for both of these data structures. The first parameter that we will talk about is the insertion operation. The process of inserting data entities in the stack is called a push operation. This operation can only be performed at the top end of a stack. For instance, consider the simulation of stack inserting few data elements. The elements that are getting inserted inside the stack are of homogeneous data type. Thus, we can say that stack can only store one type of data element. The insertion of elements in a queue data structure is referred to as an enqueue operation. It gets executed at the rear end of a queue. The simulation given in this section represents the execution of our enqueue operation. The next data manipulation operation we have on our list is deletion. The deletion of data entities from stack data structure is achieved using pop operation. The deletion of data entities from stack data structures is achieved using pop operation. This operation removes the elements where a top pointer is pointing. Thus, we can say that the stack performs the removal of data entities from its top end. This simulation shows how the removal of elements happens in the case of a stack data structure. Now, let's move to the deletion in queue data structure. The process of deleting data elements from the queue data structure is called dequeue. This operation is usually performed at the front end of a queue. The simulation given below represents how deletion happens from the front end of a queue, abiding with the first in, first out principle. Both of the data manipulation methods we reviewed earlier can be matched with previous real-life examples. What I mean by that is, the book stacking system can only place books at the top end as well as it can remove them from the top end only. Furthermore, the waiting queue analogy is deemed to be consistent with queue data structure because it adds people from the back end and removes them from the front end. Now here's the interesting question that we want y'all to answer. So, until now we have understood the structural differences between stack and queue data structures, and both of these data structures can be implemented using static or dynamic data structures. So based on your comprehension of these data structures, which implementation strategy for constraint memory management is the best choice? The first option is array implementation static, and your second option is linked list implementation dynamic. Do think and answer. It will be interesting to see how many of y'all will get this right. So guys, leave your answers to this question in the comment section below. In a week's time, we will be announcing the right answer and y'all can check it out. So moving ahead, we will discuss about the pointers maintained in the case of both these data structures. For stack data structure, our ADI only remembers one location, that is the address of the topmost element. This tracking of a topmost element is achieved using one pointer, which we name as a top for our convenience. Whereas in the case of queue, we maintain two pointers named front and rear. The rear pointer points to the last inserted element in the queue, and the front pointer points to the first inserted element in the queue. We use and maintain these two pointers to execute different operations at both the front and rear ends. The last parameter that we have for differentiating stack and queues is when to use which data structure. The stack data structure is mainly used to solve problems that are recursive in nature. For example, memory management in programming environments. The resource allocation and execution of the programs is a repetitive process based on the invocation of different function calls. And stack is the basic memory management architecture for any modern computing environment. A stack is at the heart of the runtime environment for Java, C, C++, Ada, Fortran, and other languages which is independent of their native codes like x86, Sun, or VAX. The Stack Memory Management Unit is compatible with old and new operating systems, including Windows NT 10, Solaris, and Linux runtime environments. The next applications of the stack on our list are expression handling and backtracking algorithms. The expression handling algorithms evaluates the output for arithmetic operation closed inside the parenthesis. The stack data structure is also used to perform expression conversions as infix to postfix, infix to prefix, postfix to infix, or prefix to infix. Furthermore, the backtracking algorithm is also implemented using a stack. This algorithm moves backwards and performs steps to evaluate a more adept solution. Now let's discuss about when to use queue data structure. The queue data structures work on sequential processing of data. Hence, whenever your application needs a sequential processing, a queue data structure can be implemented. For example, queue is used in messaging applications. You are probably aware that we all rely on messaging apps like WhatsApp, Facebook Messenger, and Instagram Chat to interact with our friends and family. And you must have noticed that the person you are attempting to communicate receives messages in the same sequence as you have sent them, irrespective of whether he's online or offline. Actually, the queue is implemented in messaging applications at the user's end, containing the messages to be delivered to the user. So when the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. The next application of queue is its use in operating systems. Multi-user, multi-programming, and time-sharing environments are common in today's computers. In this OS setting, a system handles multiple jobs at once, and the concept of a queue is employed to manage these activities. So, remember guys, you can implement stack data structure to solve recursive problems and queue data structure to solve problems that need sequential data processing. Queue implementation using array. First, we are going to take a small recap on queue in data structure. We then dive into the declaration of a one-dimensional array and pointers for queue implementation. Finally, we will formulate code for queue data structure using the C++ coding language. On that note, without any further ado, let's get started with a recap on queue in data structure. In the last session, we introduced you to queue data structure as an abstract data type. As we know, when we talk about data structure as ADT, we define it as a mathematical or logical model. We specify all the features or operations available with the data structure. So considering that we learnt a few basic features of a queue in the last session, let's go ahead and learn more. A queue is a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. Additionally, the queue works with the restriction that insertion should be performed at the rear node and deletion at a front node. Those processes of insertion and deletion are called enqueue and dequeue respectively. We discovered both of these operations along with three more supportive procedures named as peek, isFull, and isNull. Now that we are considering to implement a queue data structure, so all these operations will become different functional blocks. Additionally, all these operations must take constant time, and it must not depend upon a variable like the number of elements in queue or the size of the queue. By that, what I mean is the complexity of all these operations must be O of 1. Having said that, let's dive deep into the strategy to implement queue data structure. Until now, we have understood that queue is a special kind of list with some restrictions on insertion and deletion. And there are two approaches to deal with queue implementation. The first one is array-based and another one is linked list-based. In this session, we are going to focus on array-based implementation. Initially, let's say we want to create a queue of integer elements. For that purpose, firstly, it is essential to declare an array of random spaces. Let's take 100 as the size of our array. That means our array can have a maximum of 100 integer elements. The declaration of an array is made with this line of code, int q100, where int represents integer data type and q is the name of our array, and 100 is its size. The array that we just initialized is going to store our queue. By that, what I mean is at any random index of an array queue is going to start with two marked-ends, front and rear. In this array, I'm showing front of the queue towards the left and rear towards the right. For making those end nodes, we need to initialize two pointers, front and rear. At this moment, as our queue is empty, so both of those pointers should point towards -1. So initialization of these pointers should be done as int front is equal to -1 and int rear is equal to -1. When the insertion or deletion happens in queues, these pointers will be either incremented or decremented, so they are an essential part of this queue implementation process. Now you must be clear with the array and pointers declaration part. So let's dive further and formulate code for queue implementation using a one-dimensional array in C++. It is essential to include header files into our source file as we cannot access standard C++ functionalities without them. That is why here we are going to load IOStream and standard input-output files along with using namespace std. Once this is done, we will initialize our array along with front and rear pointers. Remember, we always have to declare the size of an array before compilation. That means we cannot update the size of an array at runtime. This scenario is the biggest limitation of queue implementation using arrays. Having said that, let's proceed with pointers declaration. Now we are done with the initialization process. We will now work on implementation of queue functionalities. Let's first work out supportive queue functions like isNull, isFull, and peek. isNull function validates if the queue is empty. And as per our previous discussion, when both front and rear points to -1, then the queue is considered to be empty. So the condition to determine if queue is empty will be if rear is equal to -1 and front is equal to -1, it will return queue is empty. If the queue does not satisfy the previous condition, then it is not empty. So by using the else condition, we can display the queue is not empty. Next up is isFull function. This function validates if the queue is full, and we can clearly say that if the rear pointer is equal to the max size of the queue, then our queue is going to be completely full. Next is peek. The peek function extracts the element where the front pointer is pointing without removing it from the queue. For this functionality to work, our queue must contain data elements in it. What I mean is our queue should not be empty. If our queue is not empty, then data at the front node can be accessed. This is how we implement supportive queue functions. Let's immediately dive into the development of main queue operations, enqueue and dequeue. For enqueue operation, if the queue is full, then our function should prompt an overflow error. For that to happen, we have to put this condition. If the front pointer is pointing to -1, then we have to increment the front pointer to 0 manually. Otherwise, it can be incremented by rar ++. After pointer incrementation, we have to ask for a data element to enter into the queue. Once the data is given, it should be inserted at the position where the rar is pointing now. Finally, let's code the final main queue operation called as dequeue. If the queue is empty, then there is no element for deletion, so it should prompt an underflow error on screen. Also, if there is only one element left inside queue, then both pointers should again be pointed towards -1. For that, let's write another condition here. If both the previously mentioned conditions are false, then deletion of an element can be achieved by just pointer incrementation. We have implemented all the queue functionalities here, but we haven't implemented a function that can show us how our queue looks. So for that, let's implement one more function with the name display. This function should prompt the elements of the queue on the screen. Elements will only be printed if the queue is not empty. Hence, we have to check for the emptiness of the queue first. Finally, we are done with the hard part. So let's arrive at the main function to contemplate these operations in order to visualize outputs. We are going to use a switch case to take a user command. Thus, not to waste your time on this, let me just get done with this block ASAP. That's all, we are done with the queue implementation using arrays. Let's just examine if our code works fine or not by compiling it. This program should return a console that asks the user to give commands for performing different operations. So as you can see on your screens, if I input 1, I can perform insertion in a queue. Let's perform some insertions now. We will insert 4 elements, first 3, then 21, next 78, and finally 12. After inserting these elements, we will print the state of the queue using case 3. Now let's also check the dequeue function. If we perform a dequeue operation, then 3 should be removed from the queue. Let's check if it is removed using the display function. And yes, our code works just fine. Now if you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. Additionally, you can also try to run it on your local system to have a better understanding of the concept.
We will be discussing about queue implementation using linked list. At first, we will quickly revisit the queue functionalities that we have covered in previous sessions. Followed by that, we will understand the need for linked list implementation of queue. Advancing ahead, we will deal with representation of queue using linked list and the challenges that occurs while implementing queue using linked list. Finally, we will cover the coding implementation of queue data structure. I hope I made myself clear with the agenda. Now let's get started with our first topic, which is quick recap on queue functionalities. Queue, as we know from our previous discussions, is a structure in which whatever goes in first comes out first. For example, customer service queue. In a customer service queue, the customer who enters first will leave the billing line first, and the customer who enters last will definitely get served at last. This scenario for insertion and deletion is also known as first in first out principle. Moving ahead, let's discuss some features of this queue data structure. Basically, queue is a linear data structure that follows certain restrictions on insertion and deletion. The insertion can only be made from one end and deletion can only be performed from another end. Further, deletion is called as dequeue and insertion is called as enqueue. Along with these two primary queue operations, there exist 3 more supportive queue operations named as peek, isFull, and isEmpty. Peek operation should simply return the element at the front without removing it from list, and isFull and isEmpty operation should return the state of queue that is empty or full. All these discussed operations must take a constant execution time. By that, what I mean is the time complexity for all these operations should be big O of 1. Now moving ahead, we shall understand the need for linked list implementation of queue. When we discuss the implementation of queue using arrays, we discuss the limitation of fixed size. According to that limitation, an array will always have a fixed size and it should be declared before the compilation of program. Furthermore, once all the positions in an array are taken or it is exhausted, then we only have 2 options. We can either deny insertion by saying that the queue is full and we cannot insert anything now. Or what we can do is we can create a new larger array and copy elements from the previous array to the new larger array. The time complexity for this copy operation will be proportional to the number of elements inside filled array. In other words, we can say that the time complexity of this copy operation will be big O of n. But again, as we are giving random larger size to the array, there is a possibility of massive memory loss. Like right now in this array, 70% of the memory is unused, and the memory is a crucial resource that we should always be protecting. It's not that some amount of unused memory will be a real problem in today's modern day computer, but it's just that while designing solutions and algorithms, we should always analyze and understand these implications regarding memory. Along with this memory wastage, there exists another sort of memory management issue that occurs while utilizing an array to implement a queue data structure. The space of an array which is used to store elements can never be reused to store the queue elements, because items can only be inserted from the front end, and the front end's value may be so high at that time the space before the pointer will be lost for eternity. Let's have a look at an example to understand this drawback more clearly. In this example of array representation of queue, a queue of size 10 having 5 elements is shown. The value of the front pointer is 5. Therefore, we cannot reinsert values in the place of already deleted elements before the position of front. That means the space of the array before front pointer can never be reused for storage purpose. These drawbacks represent the need for a more appropriate method to implement queues, and by using a proper dynamic data structure like linked list, these drawbacks can be easily removed. On that note, let's discuss about the representation of queue using a linked list. A linked list, as we know, is a collection of data elements that we call nodes. These nodes are stored at non-contiguous locations in memory. Further, each node contains two fields, one to store data and another to store the address of next field or the reference to the next node. Let's assume that the node in this figure are at addresses 200, 400 and 500 respectively. I have filled these addresses in the address field as well. The identity of the linked list that we always keep with us is address of the head node. We often name a pointer or reference variable at which we store the address as head. So now we are saying that we want to use a linked list to implement queue data structure. And the basic definition of queue conveys that a queue is a linear data structure in which insertion is performed at the rear node and deletion at the front node. It's really effortless to enforce this property of a queue in linked list. We can simply pick one side of a linked list for insertion and another side for deletion. If the head node is considered to be front, then the tail node will be the rear. Otherwise, if the head node is deemed to be the rear, then the tail node will be the front end. Whatever side we are picking for whatever operation, we just need to make sure one thing, and that thing is the operations that we are carrying out must take a constant time, or in other words, their time complexity should be big of 1. I hope that you guys are clear with the representation of a linked list as a queue data structure. Now moving forward, we will discuss about its implementation. But before that, let's have a look at the time complexity management challenge which occurs in queue implementation of a linked list. In the case of linked list, the cost for insertion or removal from the head side is big of 1, but the cost for insertion or removal from the tail side is big of n. So here is the deal. In a standard implementation of queue using linked list, if we insert element at one side and remove them from other side, then one of these operation NQ or DQ, depending on how we are picking this side, will cost us big of n. But the requirement that we have specified before for queue implementation suggests that both these operations must take a constant time. So we'll definitely need to do something to ensure that both NQ and DQ operations take constant time. Let's call this side front and this side rear. So I want to NQ a node from the tail side and I want to perform a DQ at the head side. We are good for DQ operation because removal from the front will take a constant time, but insertion or NQ operation will be costing us big of n. Let's first see why insertion at the tail will be costlier, and then maybe we can try to do something. To insert an element at the rear end, what we will have to do is, first we'll have to create a node. Let's say I got this node at address 350 and the integer that I want to NQ is 7. The address part of this node can be set as null. Now we have to build a link with this created new node, and to do that, first we'll set the address part of the last node as the address part of this newly created node. But the only identity that we always keep with us in case of linked list is address part of head node. So to get appointed to any other node, we need to start at head. That is why first we'll create a pointer variable temp and we'll initially set it to head node. And now using this temp pointer, we'll traverse to the end of our linked list, that is the tail node. And here using this pointer temp, we can write the address part of the newly created node at the previous tail node to build this new link. This traversal of pointer from head to tail is taking all the time for insertion. We use a statement like temp is equal to temp.next to move the next node. What we can do is we can avoid this whole traversal with the help of pointer variable just like head node. We can call this variable tail or even rear. Let's call this variable rear for now, and also the variable with storing an address of head as front. In any insertion or removal, we'll have to update both front and rear now. But from now on, whenever we will perform enqueue operation, we can directly check where a rear node is and update its address to formulate a new insertion link. This simple addition of one pointer resolves our problem with the cost of insertion. Let's understand this scenario with the help of an example. Previously, we were traversing from head node to the tail node, but now, as we know the location of tail node, there is no need for any traversal. We can directly update the address part of rear node to make a link for new node. Here, the new node with data element 7 will be linked to the previous node, and the rear pointer will also be updated to point towards the newly inserted node. Now, the complexity for both the operation will be big of 1, which means we can now begin with the coding implementation of queue using a linked list. So, let's dive directly into that. In order to get started with our coding implementation, we'll need to load some dependencies that are called as header files. I have already included those header files here. So, first of all, we'll declare a structure to create nodes for our linked list. And inside this structure, we'll initialize data and address part. So, let's get started with creation of this structure. Struct node. Now, the initialization of data and address part. Int data struct node star next. Now using this created structure, we will initialize front and rear pointers. So let's create this front and rear pointer. Struct node star front is equal to null. Similarly, struct node star rear is equal to null. The declaration of variables that we have done here is in global scope. The reason behind that is to make sure that these variables will be accessible to all the functions. So moving forward, let's work out the primary queue operation. We'll start with enqueue operation. So let's create a function for that. Void enqueue, and inside this function we'll pass an argument int x to insert an element. Now inside the enqueue function, we'll take an integer as an argument. In this function, we'll create a new node for purpose of insertion. So let's create that new node. Struct node star temp is equal to struct node star malloc size of struct node. So with this size of function, we have allotted the size of address part as well as the data part. One more thing I want to tell you guys is I am using malloc in C here for dynamic memory allocation. If you want to implement this code using C++, then you can use new operator instead of malloc. The purpose of using malloc here is to create a node in dynamic memory. Now, moving ahead, we can start working on two cases of enqueue operation. Primarily, there won't be any element inside the queue. So for the first insertion, we'll manually set both front and rear to the address of this newly created node. So to do that, first we'll have to create a if condition. If front is equal to null and rear is equal to null, front
is equal to rear is equal to temp, which is nothing but the new created pointer variable, and will return the control. If this condition fails, that means there are already some elements present inside our queue. So using else condition, we can write another statements rear dot next is equal to temp, and rear is equal to temp. Basically, these two lines of code are just updating the address part of the next node along with setting the temporary data into rear node's data field. This code will be further clear if I'll show things moving in simulation. So let's revisit PowerPoint for that purpose. Let's say initially we have an empty queue, so both front and rear will be null. Null is only a macro for address 0. At this stage, let's say we are making a call to enqueue function passing number 2 as an argument. Now let's go through the enqueue function and see what will happen. First, we'll create a node. The data part of this node will be set as 2 and the address part will initially set as null. Let's say we got this node at address 100. So a variable named temp will store this address. Right now, the front and rear both are null. So we'll go inside this if condition and simply set both front and rear as 100. After the first enqueue operation, our queue will look like this. Let's say we are making another call to enqueue function at this stage, passing number 4 as an argument. Once again, a new node will be created. Let's say I got this new node at address 200. This time the queue is not empty. So in this function, we'll first go to the statement rear.next is equal to temp. So we'll set the next part of this node at address 100 as the address of a newly created node, which is 200. So we'll build this link now. And now we'll store the address of this new rear node in this variable named rear. So this is how my queue will look like after the second enqueue operation. I hope that you guys are clear with the implementation of enqueue operation and the working of its code. Let's deal with the next queue operation named as dequeue in our code editor. Now inside this dequeue function, I'll create a temporary pointer to the node in which I'll store the address of the current front or head node so that we can directly delete it. So the statement I'll write for that is struct node star temp is equal to front. Now the first condition that we'll write in this dequeue function is underflow error. So let's begin with if block. If front is equal to null, printf queue is in empty state /n and return the control to the next function. Otherwise, in next case, when both front and rear will be equal, we'll set both these pointers to the null manually. So to do that, we'll insert another if block. If front is equal to rear, front is equal to rear is equal to null. This if block will get activated when there is only one element inside the queue. In all other cases, we can simply make a front point to the next node. So we'll simply do a front is equal to front.next. So for that, we'll write else block, else front is equal to front dot next. In all three previous mentioned cases, we are trying to remove elements and that can only be done by implicit call of function free. So let's call function free to delete the front node from our queue. So the statement that we'll write is front free the temporary variable which is actually storing the head node address. Next, we'll work on peek operation, and for that we'll create a new function int peek. Basically, the peek function is used to extract a value of print pointer. For print pointer, we will simply check if the queue is empty. If it is empty, then obviously there is no element at front node to extract. But if it is not empty, then we can extract a value from print pointer. So for that, we'll create a if block if front is equal to null, which also means the queue is empty. Then we'll return printf queue is empty /n. Otherwise, we will return the data present at front node. Now we have implemented all important queue functionalities, but we won't be able to check the state of queue with the help of these functions. So let's formulate one more function called as print to visualize our queue. So let's define this function void print Inside this function, we'll create a temporary pointer struct node star temp is equal to front. We are initializing this temporary pointer to the front so that we can traverse the whole queue elements using iterator element. So moving forward, let's create this iterator element using a while block. So the statement that we'll write for that is while temp is not equal to null, printf modulus d comma temp dot data. And we will set temp is equal to temp dot next. This is nothing but the traversal of linked list. Now we'll also printf /n so that all elements will be printed in order. With this, we have completed the implementation of print function as well. Now let's work on our driver method called as main function to contemplate the output of our program. Inside this, we'll make call to the enqueue function enqueue to, and we will print the state of our queue using print function. Next, we'll make call enqueue for, and we will also print the state using print function. Next, we'll make call to enqueue 6, and we'll also print the state of our queue at this instance. Now, after this, we'll dequeue few elements, dequeue, and we'll print the state. Next, we'll enqueue one more element, enqueue 8. Now that we are done with the coding implementation of queue using linked list, let's execute the program and visualize the output. This is the output that we have received. Let's compare it with the calls that we have made in order to judge its correctness. The first call that we made was enqueue2. So the print function has printed 2 over here. After that, we inserted element 4 and 6, and our print function has printed the state after these operations as well. Next, we deleted the element present at front pointer, which is 2. So after deleting 2, the output that we got is 4 and 6. Finally, we inserted one more element to check if it is getting inserted at the rear end, and that element was 8, which is exactly inserted at the rear end of queue.
We will be discussing about circular queue in data structure. So at first, we'll discuss why the concept of circular queue was introduced. Followed by that, we will understand how we can represent a circular queue using an array and linked list. Advancing ahead, we'll deal with the implementation of a circular queue using array and linked list. And finally, we will cover the applications of a circular queue to understand its importance. I hope I made myself clear with the agenda. Now let's get started with our first topic, which is why the concept of circular queue was introduced. In our previous sessions of queue implementation, we discussed the challenge of memory wastage while operating on linear queue. And as per our previous discussions, we know that memory is a crucial resource that we should always be protecting. It's not that some amount of unused memory will be a real problem in today's modern day computers. It's just that while designing solutions and algorithms, we should always analyze and understand implication like memory usage as well as the time taken for execution. In the case of linear queue, we have already learned that insertion is done at the rear end and deletion is done at the front end. Initially, when the queue is empty, both of these pointers point to null memory space, that is -1 according to our convention. But as we keep adding elements into the queue, the rear pointer keeps incrementing until it reaches the max size of the queue. In this particular example of the queue, the new data element will be inserted after each incrementation of a rear pointer until the pointer reaches the end of a queue. When the front pointer remains pointing at the exact same location until we perform dequeue operation. But here comes the challenge. When we perform those dequeue operations, the empty space gets created at the starting part of the queue. And there is no way we can reutilize this blank space as the rear pointer has already reached the end of queue. So to overcome this limitation, the concept of a circular queue was introduced. A circular queue is nothing but the extended notion of a linear queue, as it also follows the principle of first in first out, with the exception that the last position of this particular queue is connected to its first position, making a circular link. This circular link is responsible for naming of this queue as a circular queue or a ring buffer. Additionally, this new circular link feature resolves the problem of memory wastage in a linear queue. Let's understand how this problem is actually getting resolved with the help of an example. This figure is an illustration of a circular queue having size 5. The element at the front node is 7 and the element at the rear node is 9. As we can clearly see, this queue is completely filled, and if we try to perform enqueue operation, it will definitely return an overflow error. We can only perform a dequeue operation on this queue. But if we perform dequeue operation, the front pointer will be updated to point to the next available data element. Further, due to this dequeue operation, the empty space will get created in the beginning part of a queue. But because of the circular link, rear pointer can arrive back at the empty space for making insertion of a new data element. Hence, the circular queue concept is better version of a queue data structure considering its benefits over a circular queue. Moving ahead, we'll discuss how we can represent a circular queue using an array and linked list. However, initially we should also look into the principle of circular incrementation, which drives the insertion in a circular queue. The circular queue incrementation is a process of pointer incrementation that allows rear pointer to arrive back at the beginning part of a queue once it reaches the max size of queue. Let's understand how circular incrementation works with the help of an example. The simulation of a circular queue shown here has max size 6, which means it can store 6 data elements. In the first scenario, when queue is empty, It can store elements by simply incrementing the rear pointer as shown in the animation. The other scenario for insertion in queue is when the rear pointer is at the end of queue and there is an empty space at the beginning portion of a queue due to dequeue operations. In this case, the rear pointer can arrive back at the beginning of queue to insert a new element at any empty space. But the biggest question that arises here is how the circular incrementation is happening logically or arithmetically. Let's contemplate the logic for this process of circular incrementation with the help of previous example. In the last example of a circular queue, the max size of a queue was 6 and rear pointer was pointing to the index 5 where front pointer was pointing to index 2. Now for the new incrementation to happen, we have to bring rear pointer to the index 0. Let's analyze how we can do that. If we simply add 1 to the rear pointer, then we will get 6 as a result, which is also the max size of our queue. Now, if you guys remember the modulus operator in programming, you can clearly achieve the circular incrementation. For example, in this case, rear plus 1 modulus max size will output 0, the result which we want. So, with the help of modulus operator, we can perform the circular incrementation to formulate a circular link using arrays. Now that you have understood how circular link is implemented in case of array implementation of circular queue, we will now look into representation of a circular queue. In the array representation of circular queue, you can clearly see that the last index of the array is connected to the first index by circular incrementation process. Moving forward, we'll look into the different cases of inserting an element into the queue. The first case that we are going to discuss is to determine if the queue is full, as we cannot insert a new element into the queue when it is full. But how can we judge if the queue is full? Well, that's quite easy. If the result of circular incrementation matches to the index value of front pointer, then there is no space for insertion of a new data element. That means if rear plus 1 modulus max size is equal to front, then the queue is full and insertion cannot be achieved. The next case for inserting an element into a circular queue is when there is space at the beginning of a queue. Let's say the size of an array is 5, in which the rear pointer is pointing to the index 4 and the front pointer is pointing to index 2. By making circular incrementation, we can insert element at the empty space. By using rear is equal to rear plus 1 modulus max size statement, we can bring our rear pointer to the beginning part of our queue to make a new insertion. That's all about array representation of a circular queue. Now moving ahead, we will discuss the representation of circular queue using a linked list. The linked list representation of a circular queue can be achieved by changing the reference field of the tail node. For that, we can just add the address of head node in the reference field of the tail node. The implementation of a circular queue using linked list is more efficient than array implementation as it manages memory more effectively. Further, it is a dynamic structure that can be allocated with more memory space if required at the runtime. On that note, we have covered the representation of circular queue using both arrays and linked lists. Now, we will implement a circular queue using both of these data structure with the help of C programming language. First, let's dive into the array implementation of a circular queue using the C programming language. For that, let's visit our code editor and get started. The program for array implementation will begin with the declaration of array and pointer variables. So let's create an array first, int a, close braces and semicolon. Now the size that we want to allot to this array is 5. So let's define our max size value as 5 first. Hash define max underscore size as 5. Now let's pass this as an argument to this array. Now we will define the pointer variables as well. So int front is equal to -1. And also the rear pointer Okay, now we have successfully created our array and pointer variables. So after this, we'll begin with the implementation of circular queue operations. The first primary queue operation that allows us to manage data flow in a queue is enqueue. So we will create this function first. Void enqueue, and we'll pass an argument variable x to insert an element. For implementing this operation, we have to check if the queue is empty. If a circular queue is empty, then we'll set both the front and rear pointer to 0 manually. For that, we'll write a statement if front is equal to -1 and rear is equal to -1, then set front equal to rear equal to 0. We have just written the condition for instance when the queue is empty. Next, we'll write the condition to check if the queue is full. So for that, we'll create else if condition, else if rear plus 1 modulus max underscore size is equal to front then printf queue is full /n and return the control to the next function. If both these above mentioned conditions fail, then we'll have to increment the rear pointer using the technique of circular incrementation. So for that, we'll create another else loop. Else rear is equal to rear plus 1 modulus max underscore size, and outside this we'll make an insertion into our array. With this, we have successfully created our enqueue operation. Now we'll move towards the dequeue operation. For that, we'll create another function, void dequeue. The dequeue operation is responsible for removing the element from the front node of a queue. Further, an element can only be deleted when there is at least an element to delete. So, first we'll have to check if our queue is empty or not. For that, we'll write a statement if front is equal to -1 and rear is equal to -1. Now inside this block, we'll printf queue is empty and we cannot delete any element. We will return the control to the next function. In addition to that, if there is only one element inside the queue, we'll have to set both front and rear pointer to the null manually. So for that, we'll write another condition, else if front is equal to rear, which must be the 0th index or the last element inside queue. And inside this function, we'll write front is equal to rear is equal to -1, which means we'll set it back to the null state. If both these conditions fail, then we'll simply have to increment the front pointer using technique of circular incrementation. For that, we'll write another condition, else front is equal to front plus 1 under braces modulus max underscore size. With the help of these three conditions, we'll be able to delete element from our queue. Now, moving forward, we'll look into another operation, that is print function. So let's create a new function for that, void print We will understand this function with the help of PowerPoint, cause it will be more understandable to all of you if I show things in moving simulation. So let's visit PowerPoint for that purpose. The count variable used in this print function is supposed to count the number of elements inside the queue. We'll understand how it is operating arithmetically with the help of an example. Let's say the max size of our array is 5, where front pointer is pointing to index 1 and rear pointer is pointing to index 4. To work out the value of count variable, we'll need to perform following operation. Rear plus max size minus front modulus max size plus 1 is equal to count. By filling the values in this operation, we'll get 4 as a result, which is the exact number of elements inside the queue. Now we will iterate through the queue using for loop and will also print the elements. I hope you are clear with the implementation of this print function now. Moving forward, we'll revisit the code editor to write main function and to check the result of our program in C. Inside this main function, we'll call enqueue function to insert some elements into the queue. And after few insertion operations, we'll call print function to represent the state of our queue. So let's insert few elements at first. Enqueue 5, enqueue 7. Next element that we will insert is enqueue -3. Next enqueue 0. Now let's write one printf statement. The element inside the queue are and in next line we'll return the state of queue using print function. Well, there is single mistake in this code here. We have written printf statement in uppercase, which is a case error in C programming. So we'll change it to the small p. Now we'll dequeue few elements to understand the operation of dequeue as well. So let's dequeue 2 elements one more time. And after these two operations, we'll also print the state of queue once again using the print function. Well, we'll write one more statement. Printf the state of queue after 2 deletions. And also we want this statement to come in next line, so let's write /n. Okay, So with this, we have successfully completed a coding implementation of circular queue using arrays. So let's compile this code and check if it is working fine or not. Well, here is the output that we have got. The elements inside the queue are 5, 7, minus 3, 0. So let's check our order of insertion. So we include 5, 7, minus 3 and 0. And in similar order, the elements are inserted in our queue. Also, we deleted two elements from the front node, that is 5 and 7, which are also deleted here. With this, we can say that our code works fine. So let's move towards linked list implementation of circular queue. For linked list implementation of queue, first we'll need to create structure of a linked list and pointer variables. So first we'll create a structure for node, struct node int data part and the address part. Semicolon. Now we'll create pointer variables. So for that, we'll write statement struct node star front is equal to -1. Similarly, struct node star rear is equal to -1. After done with this pointer declaration, we'll begin with the implementation of queue operations. The first operation that we'll work on is enqueue operation. For that, let's create a new function, void enqueue int x. And inside this function, we'll create a temporary node using the previous structure of node. So for that, we'll write statement struct node star new node is equal to struct node star malloc size of struct node. After creating a new node, now we will also insert values into both data and reference fields. Data will be the argument provided by the user and the reference field will be set to null initially. So let's do that here. New node, arrow operator, data is equal to x. And similarly, new node, arrow operator, next is equal to 0. Now, there are two conditions for inserting a new node into the linked circular queue. In the first condition, we'll insert a new node into an empty queue. In this case, both the front and rear pointer must be null. So let's write a condition for that. If rear is equal to -1, then front is equal to rear is equal to new node, and rear dot next is equal to front. Now, in the second case, the queue already contains more than one data element. The condition rear is equal to -1 becomes false. In this scenario, we'll just update the rear pointer to point to the new node. For that, we'll create a else block, else rear dot next is equal to new node and rear is equal to new node, where rear dot next is equal to front. With this, we have successfully implemented our enqueue function. So now let's move towards dequeue function. For that, we'll create a new function, void dequeue, and inside this function body, we'll also create new temporary pointer. So let's create that struct node star temp, and we'll set this temp is equal to front so that we can delete it from our queue. Next, we'll build a condition for deletion. The first condition that we'll check is if our queue is empty or not. For that, we'll write statement if front is equal to -1 and rear is equal to -1. If this condition becomes true, then we will printf queue is empty. Let's add slash in here so that it gets printed in next line and semicolon. Okay. Further, if there is only one element in the queue, then we'll set both front and rear pointer to the null manually. So for that purpose, we'll create another block, else if front is equal to rear, which will happen when there is only one element in our queue. And inside this condition, we'll put front is equal to rear is equal to -1, and we will free the temporary variable, which is also storing the front pointer. Okay, now if both these above mentioned conditions fail, then we will update the value of front pointer to point to next node, and we'll also deallocate the memory of deleted node using free function. For that, we'll write another else condition, else front is equal to front arrow operator next and rear arrow operator next is equal to front, and we will free the pointer present at front node, which we have previously stored in this temporary structure. With this, we have successfully implemented the dequeue operation. Now we'll work on the display function, which will represent the state of our queue. For that, let's create new function, void display, and inside this function we'll also create the temporary node struct node star temp is equal to front. And now let's write one printf statement to display the elements in a queue. The elements inside the queue are semicolon. Now the first condition that we are supposed to check inside this function is if a queue is full or not. For that we'll write if statement if front is equal to -1 and rear is equal to -1, then printf queue is empty. Let's add /n. Otherwise we will print the elements inside the queue using while block. Temp arrow operator next is not equal to front, then printf modulus d, which is nothing but the data part of our temporary pointer, and again printf modulus d comma temp data. With this, we have successfully completed the implementation of our display function. Now next, we'll look into our driver method, that is main function. Inside this driver method, we'll call enqueue function to insert few elements. First we'll pass 5, then we'll insert -32, then 6, and we will enqueue 3 finally. Now let's print the state of queue using display function. Now after this we will dequeue few elements. And we will display the state of queue once again. But before this, we'll write one more statement, printf the state of queue after deleting 2 elements. And let's add /n so that this statement gets added to the next line. With this, we have successfully implemented our linked list implementation code for circular queue. So let's compile it and check if it is working fine or not. Okay, there are few. We have successfully implemented our code now, but the only problem we are facing here is all the elements are getting placed close to each other. To remove this close proximity, we'll have to make changes in our display function. So let's do that. We'll add space before modulus d in both the cases and again compile it. So let's run it again. Okay, so now our output looks fine, right? The elements inside the queue are 5, minus 32, 6 and 3, and after deleting first two elements that are front elements, we will remain with 6 and 3. That means the first two front elements 5 and minus 32 will get removed out of our circular queue. Okay, so we have finished the circular queue implementation using linked list as well. So let's move back to our PowerPoint presentation. The last topic that we have on our agenda is applications of a circular queue. So let's deal with this topic to understand the importance of circular queue. The first application of a circular queue that we are going to discuss about is data buffer. After that, we'll discover CPU scheduling algorithms and computer controlled traffic light systems. Data buffer is a region of a physical memory which is used to temporarily store data while it is being moved from one place to another. Typically, the data is stored in a buffer as it is retrieved from an input device such as a microphone or just before it is sent to an output device such as speakers. Basically, when the input is provided to the microphone while using applications such as Google Meet, WhatsApp, Zoom meeting, etc., then the input does not get stored in the physical memory of the device. Instead, it gets stored in data buffer implemented in this application. The data buffer will store the input signal in order and similarly it will dequeue it in exact same order, just like first in, first out circular queue. Furthermore, this data buffer is also used in internet streaming applications. Let's understand how it is used in case of one of the most famous streaming platform, Netflix. Netflix uses Amazon Cloud Services to cater for their computing as well as storage needs. The servers of Netflix are deployed over AWS Cloud, which are further connected to the content delivery network servers that are spread across the globe. These servers work together to provide fast delivery of internet content in the form of audio and video chunks or packets. These packets will be received in a virtual data buffer implemented inside MS Silverside, which is an application used by Netflix to stream content on remote devices. This buffer acts like an accordion in this streaming application. It gets filled when packets are being delivered at a rate that exceeds the video stream data rate and empties when the packets are not being delivered fast enough. The next application of a circular queue is a ready queue in CPU scheduling algorithms. CPU scheduling determines which process will own CPU for execution, while other processes are on hold. The main task of CPU scheduling is to ensure that whenever the CPU remains idle, the OS at least selects one of the processes available in ready queue for execution. The algorithm named round robin uses a circular queue to implement the ready queue state. The ready queue stores all the processes that are available for resource allocation having their own burst time. The burst time is the time that processes need to hold the CPU for their execution. But in this algorithm, the CPU has assigned with timestamp of 2 microseconds. This timestamp is the actual period for which the processes can hold the CPU for execution. So for example, the first process P1 had a burst time of 4 microseconds, but it can only access the CPU for 2 microseconds due to its timestamp. So this process will again re-enter the queue at the rear end. Further, the empty space created at the beginning of ready queue will be managed by the process of circular incrementation. This is the advantage of implementing ready queue using a circular queue. The next application is computer controlled traffic system. The circular queues are used in these systems to activate the signal lights for constant intervals of time. The computer system used for traffic light control stores a circular queue containing the commands to lit the traffic lights. These commands will be activated for a certain amount of time and will be reinserted at the rear end of a queue. This process is an example of circular FIFO principle, which is followed in insertion and deletion for circular queue. We will be discussing about priority queue in data structure. We'll start this discussion with introduction to the priority queue. Followed by that, we will understand how we can represent a priority queue. Advancing ahead, we'll deal with different implementation strategies for priority queue. After that, we'll understand what is a heap data structure and what different types of priority queue are available. Followed by that, we'll contemplate different operations in priority queue. Once finished with that, we will implement a priority queue using heap data structure. And finally, we will cover applications of priority queue to understand its importance. I hope I made myself clear with the agenda. Now let's get started with our first topic, Introduction to Priority Queue. Primarily, we will have a look at the real-life example of priority queue to understand it better. A hospital emergency queue is almost an ideal example of priority queue. When you go to the hospital, you must have observed that the person who needs immediate medical attention will be treated first, irrespective of his arrival at the reception. That means treating a person who is in agonizing pain or in emergency medical condition is the priority of the queue of patients. Priority queue in computer science also works with same approach. So what exactly is this priority queue? Well, a priority queue is an abstract data type that operates similar to the normal queue except for the fact every element has certain priority assigned to it. This definition of priority queue suggests that this particular type of queue also follows the same restrictions for insertion and deletion of data elements. The insertion in the priority queue will only be achieved at one end and deletion at another or opposite end. Additionally, the priority of data elements will determine the order of removal. The elements which has higher priority will leave the queue at first, and the elements which has lower priority will definitely leave the queue at last. As a side note, I would like to tell you guys that the priority queue only supports the elements that are comparable, meaning the data that we are going to insert into priority queue must be orderable. The compiler should not be facing any difficulty while comparing these data elements. Otherwise, the execution of a priority queue will definitely fail. Moving ahead, let's have a look at an example of priority queue. In this priority queue, we will insert 7, 2, 45, 23 and 12 respectively. These elements are not ordered. So how the priority queue is going to store them in order? Well, at the time of insertion, the priority queue conducts a comparison of each element with every other element present inside a queue to store them in order. But as there is no element inside a queue, so the first insertion, that is an element with value 7, will be attained. Followed by that, the next element will be inserted in a queue. Since the newly inserted element is smaller than that of previously inserted element, we'll swap their positions in order to maintain order. Remember, the element with least value will have a higher order and the element with greatest value will have a least priority or order. Now we will insert the next element in a queue, that is 45. As 45 is a larger element than the elements inside the queue, there is no need to shuffle elements. When we make the next insertion, the element 32 will get inserted at index 3. Now this element is smaller than that of 45. So the algorithm will have to swap the locations of these elements. Now we will perform the final insertion into our queue. We will insert 12 at index 4 now. But as you can see, this element is smaller than both the previous elements. Thus the algorithm will have to swap their positions. Now 45 will reach the end of queue as it is the element with highest value, and 2 will remain at the front of queue as it is the least valued element. As a humans, we could see the numbers visually inside the priority queue, and further we can easily arrange them. But how does the machine know this? Does it restore all the elements inside the priority queue before each insertion? No, obviously that would be highly ineffective as there will be n comparisons for insertion of n elements, leading to time complexity big O of n square. This is an enormous time complexity which we cannot allow in any software application. We will understand how the priority queue manages to reduce this time complexity
in upcoming topics. But right now we will contemplate different properties of a priority queue that we have learned from previous example. The first property of priority queue suggests that each element has a certain priority assigned to it. That priority might depend on value of data element. It can be either larger or smaller. The next property states that element with higher priority will leave the queue at first, where the element with least priority will leave the priority queue at last. Further, if two elements have the same priority, then the element will be removed from the priority queue based on their arrival. That means the element which arrived at first out of the elements having same priority will be removed first. Now, moving ahead, we'll deal with the representation of priority queue using a linked list, as usage of arrays is not an ideal way to implement priority queue. If we consider array implementation of priority queue, then inserting items into the sorted array will cost us big O of n, and in general, processing each element will further cost us big O of n square as discussed previously. So in this tutorial, we'll just look into the linked list representation of priority queue. We will understand the representation of priority queue with the help of an example. Initially, let's say there are 3 elements inside a linked priority queue and all of them are in order. 3 being the least element has highest priority, where 43 has the least priority. The purpose of keeping 3 at the head node is that we want our priority queue to delete elements according to their priority. Now, we want to insert a new node consisting of data element 2. And as the data element is smaller than the element at head node, that is 3, so this new node should be inserted prior to it. This particular scenario of insertion seems pretty perfect as it does not cost us more time. But what if the element is significantly larger than all the nodes in queue? For instance, let's say we want to insert 45 as a new element. In that case, primarily it will be compared with element 2, and as 45 is larger than 2, our temporary pointer will move to the next node for comparison. Now, 45 will be compared with element 3, and again the temporary pointer will be moved to the next node for comparison. After 2 comparisons, the temporary pointer has reached element 17 for performing the next comparison. And here also 45 is larger than 17, so the temporary pointer will again move towards the next node. Now finally, our temporary pointer has arrived at the tail node consisting of element 43. Again, in this case, the element 45 is larger than 43, thus the new node will be inserted after node containing data element 43. From this specific example of insertion into a priority queue, we can clearly see that there are n comparisons leading to the time complexity big O of n, where the complexity of deletion remains constant, that is big O of 1. While understanding the representation of priority queue, we came across some facts that make priority queue implementation using linked list quite vulnerable. So here we will again try to recall them. The first drawback of priority queue implementation using linked list is that it costs us big O of n for inserting a new element. Further, it also costs us big O of n for peak operation. And as memory and time management is the purpose of data structure, hence we must try to analyze other implementation strategies. That is why in upcoming slides we'll look into different approaches to implement a priority queue. There are 3 approaches that implement a priority queue with complexity less than big O of n square. We have already discussed the linked list, so let's also look into other 2 approaches. Binary heap and binary tree provides almost similar complexity. These approaches cost us big O of log n for insertion and deletion, and big O of 1 for peak operation. But which one of these operations is most optimal approach to implement priority queue? Well, to answer this question, we again need to discuss about memory management in the case of both these data structure. You guys know that binary heap data structure is implemented using arrays, and since it utilizes arrays, there is always a better locality of reference as well as operations become more cache friendly. The binary search tree uses pointer to implement front and rear node, which definitely takes up more space in memory. Due to that, building a self-balancing BST cost us big O of n log n, where binary heap just cost us big O of n. These facts
clarify that the binary heap is the base data structure to implement a priority queue. Now you must be thinking about what exactly the heap is and how does it work. So moving forward, we'll look into the definition of heap and its properties. Basically, a heap is a tree-based data structure that satisfies the heap invariant, or in simpler words, heap property. The heap invariant states that if A is a parent node of B, then A is ordered with respect to B for all nodes A and B in heap. What that means is the value of parent node is always greater than or equal to the value of child node in the heap, or other way around, the value of parent node is less than or equal to the value of child node for all nodes in a heap. Further, there are two types of heap named as max heap and minimum heap. First, we will look into max heap. The max heap is heap in which value of parent node is greater than the value of child node. For this particular example of max heap, you can see that the root node is the biggest element in tree and each child node is smaller than its parent node. The next type of heap is minimum heap. The min heap is heap in which the value of parent node is less than the value of child node. In this specific example, you can observe that each child node is larger than its parent node and the element at the root node is smallest element of the heap. Both the structures that we have discussed are binary heaps as every node has only two children. In upcoming slides, we will discuss some complex structures of heap data structure to better understand how we can judge if a tree-like structure is heap or not.
Okay, so you can see a tree-like structure on your screen and we are supposed to check whether if it is a valid heap data structure or not. But actually here I would like you all to give it a try by yourselves. You can also pause this video if you want, but here I will provide you with a short moment to inspect this structure. Alright, I can clearly say that this is not a valid heap data structure. As you can observe, the highlighted part is violating the heap invariant. Moving forward, let's analyze another tree-like data structure to consider if it is a valid heap or not. Well, yes, this is a valid heap because even though this one is strangely structured, we are free to move around the visual representation of nodes to make it organized. Now you all must be thinking how we can do that. Well, we'll understand that scenario in upcoming slides. Now, how about this one? Is this a valid heap? No, right? This is not a valid heap. This structure is not even a tree as it forms a closed cycle and every heap must be a tree. So it's pretty clear that this is not a valid heap. Now, what about this one? Is this a valid heap? Yes, this is a valid heap as it satisfies the heap invariant that all the child nodes must be greater than or equal to or smaller than or equal to its parent node. Now, this is the last structure that we are going to check if it is a valid heap or not. What you guys think? Is this a valid heap? Well, I think it's pretty clear that this is not a valid heap, but it can be converted into a heap by making a one small change. Now, if we make 6 as our root node, then this structure will get converted into a max heap, which is absolutely a valid heap. I hope you all are clear with the heap invariant and how to judge if a given tree is a valid heap or not. Now moving ahead, we'll discuss the different types of priority queue.
Basically, there are two types of priority queue based on the priority of elements. If the element with smallest value has highest priority, then that priority queue is called as min priority queue. And if element with higher value has the highest priority, then that priority queue is known as max priority queue. Furthermore, it's vividly clear that the min priority queue can be implemented with a minimum heap, where the max priority queue can be implemented using maximum heap. Moving ahead, we'll deal with the operations in priority queue considering the heap as implementation strategy. The common operations that we can perform on priority queue are insertion, deletion, and peek. But there is one more hidden additional operation that gets performed during these operations. That operation is called as heapify. Heapify manages the priority of data elements in a heap by shuffling the data elements after new insertion or deletion. First of all, we will understand how insertion in priority queue happens with the help of an example. In this example, we are inserting a new data element that is 43. But due to this insertion, the structure disobeys the priority queue invariant that the parent node of the max priority queue must be greater than its child node. Now, the heapify operation solves this problem by rearranging data elements by carrying out the comparison. In this particular case, 43 becomes the parent node where 40 becomes the child node. The next up is deletion. As we know, the highest priority element will be the first to leave the priority queue, and further, it is stored at the root node of a max heap. So definitely, the element present at the root node will get removed. But due to this operation, the order of priority queue gets affected. However, the heapify operation comes to the rescue. It reshuffles the elements of the priority queue to rearrange them in order. The next operation that we are going to discover is peek. The peek operation simply returns the element present at root node without removing it, and it is easily accessible. Thus, the time complexity of this operation is big of 1. I hope you all are clear with the operations that can be performed on priority queue. Moving forward, we'll try to implement them with the help of minimum heap. As discussed earlier, while implementing a heap data structure, we know that all the elements will get stored in an array, and we don't have any pointers pointing to either child or parent nodes. So how exactly does the heap data structure remember nodes like parent nodes and its left or right nodes? Well, if you have learned binary trees, then you must know the formulas present on your screen. These formulas determines the left child, right child, or even the parent node of any binary tree. Let's understand how this phenomenon works with the help of an example. We'll begin with index 0. If we enter 0 in this arithmetic expression, then we will get 1 and 2 as output. That means the element at index 1 will be the left child and element at index 2 will be the right child, and tree structure will look like this. Now, moving ahead, let's take an example of index 1. For index 1, the left child will be at index 3 and the right child will be at index 4. Similarly, for index 2, the left child will be at index 5, where the right child will be at index 6. Using these formulas, we'll be implementing heapify and primary queue operations. So note them down for further reference. Now moving further, we will visit code editor to implement priority queue data structure using C programming language. Previously, I mentioned that heap is implemented using arrays. So to begin with heap implementation, primarily we will create a structure consisting of different variables or objects needed to implement heap data structure. So let's create a structure, struct heap consist int size, int count variable, and int star heap array, which is a dynamic array that we are creating here. And next, we'll also declare a pointer to heap structure along with size and count variable in a global scope. So let's do that. Int star heap comma size comma count. We'll create one more variable int initial underscore size to represent the initial size of our priority queue, and let's assign it value 4 for now. Okay. Now it's time to allocate memory to our heap array. For this purpose, we'll create a new function called heap underscore init. So let's create this function void heap underscore init, and inside it we'll pass an argument struct heap star h, which is a reference of this structure that we created previously. Okay. In this function, let's initialize the variables that we have created inside this heap structure. So for that, we'll initialize h arrow operator count is equal to 0. Similarly, h arrow operator size is equal to initial underscore size, and h array is equal to int star malloc size of int star 4. This statement is just allocating 4 integer variables to our heap array. Basically, our heap array is dynamic data structure. That's why we have to provide it with dynamic memory using malloc. If you are using C++ programming language to implement this data structure, then you can use new instead of malloc. Moving forward, now we'll work on our condition if not h arrow operator allocates memory to heap array, then printf error while allocating the memory, and that /n. Next, we will write exit command. Okay. With this, we have successfully implemented our heap init function. Now moving ahead, let's implement heapify function to move the nodes. For that, we'll create a heapify function void max underscore heapify int star data int log int count. So all these are required variables to implement this heapify function that we have passed in argument for this max heapify function. Now let's create few more variables that we need. Int left comma right comma largest comma temp. Now, as discussed earlier, left will be equal to 2 star location in array plus 1. and right will be equal to left plus 1. Now let's say largest is equal to LOC, and we'll work on conditions now. If left is greater than or equal to count, and data left is greater than data largest, that is the location we have stored in largest variable, then largest is equal to left. With this block, what we are doing is we are checking if the element at location left is greater than the element at recent position, and the value at left is also greater than the value of recent location. If these conditions are true, then we will set the recent location as left. And here we are getting signal that there is semicolon missing over here, so we'll add it. Okay, now let's work on next condition. Now we will check the value at right position. If the recent location is greater than the right and the value at right is greater than the largest value, then element at largest will be set to right. So for that we'll write condition if right is greater count and data right is greater than data largest, then largest is equal to right. Otherwise, if largest is not equal to location, then we will store the data present at location in temporary variable, and data LOC is equal to data largest. This is a swapping operation that we are carrying out here. And next, data largest is equal to 10. And now we'll make recursive call to our heapify function max underscore heapify data comma largest comma count. Okay. With this, we have successfully completed our heapify function. Now we will work on insertion operation on priority queue. Let's call this function heap underscore push, because we are treating this structure as heap, right? So in heap, insertion is called as push operation. So we'll call it void heap underscore push, and we'll pass arguments struct heap star h int value. And inside this function we'll create few more variables int index and parent. If you guys remember, the initial size that we have allocated to our array is 16 bytes. You can verify with this statement here that we are providing 16 byte size to our heap array. But what if you want to insert elements more than 4? Then what we'll do? Well, for that, we'll need to increase the size of our heap array. So we'll do that here. For this resize, we'll create if condition if h dot count is equal to h dot size, then h dot size plus equal to 1 and h dot heap array is equal to realloc h dot heap array size of int star h dot size. Basically, we are using realloc function in C to extend the dynamic memory space for our heap array. And in order to increase the size, we have to increment the size variable first. So that's what we have done in this statement here. And now, once done with this, we'll check if our dynamic memory is getting allocated or not. So for that, we'll add one more if condition inside this if block. So it can be called as nested if you guys want. Dot heap array, then exit -1. Now we'll move out of this if block and we will set index variable to h dot count plus plus. Basically, we are iterating with help of index variable here. So next we'll add for condition for loop index to index is equal to parent. And inside this condition, we'll make parent node is equal to index -1 by 2. This is nothing but the formula that we have discussed in previous part. Now we'll add one more condition inside this for loop if h dot heap array parent is greater than or equal to value, then we will break this for loop. Otherwise, h dot heap array
index will be equal to h dot heap array parent. Now we'll move outside this for loop and we'll add one more condition of insertion, that is h dot heap array, and at position index we will add the value provided by user using argument to heap push function. Okay, with this we have successfully created our heap push function. Now we'll move towards the next function, that is heap underscore delete. For that we'll create new function heap underscore delete, and let's make this function integer, and we'll pass struct heap star h as an argument. We will create one more variable temp is equal to h arrow operator heap array, and inside this we'll pass a negating index. That means we are using this temporary variable to traverse through all list of elements. So for that we'll write dot dot minus minus h arrow operator count, which will decrease count one by one. Now next we'll add condition if h arrow operator count is greater than or equal to h arrow operator size plus 2 and h arrow operator size is also greater than the initial underscore size. Okay. Then what we will do is we will set size to negate itself by 1 for each iteration, and then we will add h arrow operator heap array is equal to realloc h dot heap array comma size of int star h arrow operator and size and semicolon. So basically what we are doing here is we are checking if count is smaller than the size of heap plus 2 and the dynamic size of queue is also larger than initialized size, that is 4, then what we are doing is we are reducing the size for deleting an element using this statement, and in next statement we are reallocating that deleted space. So this is how this if block works. Now moving forward, we'll add condition
to check if memory is getting reallocated or not. For that we'll write condition if not h arrow operator heap array, then what we'll do is exit with -1. Okay, now let's move out of this if block, and now we will set this removed variable to h arrow operator heap array and index 0. So if you guys remember, 0 is the index of the highest element in our maximum heap. What I mean here is the element with highest value is stored at index 0 for max heap. Now moving forward, to delete this element, what we'll do is we will set h dot heap array and index 0 is equal to temporary variable or pointer that we have created previously, and next what we'll do is we'll call max underscore hippify function to rearrange the structure of our priority queue which has been shuffled due to this delete operation. Now for that we'll pass arguments our heap structure, that is heap array, and next the index which was removed and the count variable. And we'll return the removed element. Okay, with this we have successfully implemented our delete function. Now to understand the order of deletion in priority queue, we will implement one more function called as mtpq. So let's create this function. And in this function we'll pass the reference of heap structure in order to operate on it. So let's pass the structure heap star h, and inside this function we will create a while loop h dot count is not equal to 0, then printf modulus d and recursive call to heap delete function in which we'll pass h. Now we are done with this mtpq function. Further, we'll create one more function to visualize our priority queue. Let's call this function void heap underscore display, and inside this we'll pass structure heap star h, and now we will create one iterator element, and using that iterator element we'll create for loop I is equal to 0 to I is greater than arrow operator count plus plus I, and inside this for loop we will print the elements present in our queue using this format, modulus d, and we'll call heap array. But for that, we'll need to call structure as well. Heap array, and we'll pass this iterator variable into it. Okay, and then next we'll get outside this for loop and we'll printf this to the next line using /n. Okay, now we have implemented all the required function for our priority queue. Moving forward, we'll work on our driver function, that is main method, to contemplate the result of our program. So for that, we'll first call struct heap h, then we'll call init function to create heap structure. So heap init, and we'll pass the address of h. Next, we will call heap underscore push function to insert element, and h comma 1. Next, I'll copy this part, we'll paste it to insert another element. Now we'll insert 5 here. Next, paste, and we'll pass 3. Next, we'll insert element 7. Next, we'll insert element 9. And after this, we'll insert element 8. Okay, so now let's display the elements inside our heap using heap underscore display function. And let's pass an h object to print it. And again, we'll call empty pq function, empty pq, we'll pass h, and after deleting all elements, it will return the state of our heap array again, or our priority queue. So finally we'll add return 0 statement, and now our code is ready. So let's compile it and check it if it works fine or not. So we are getting 4 errors here, guys, so we'll need to resolve them. First, we'll need to check line number 82. So for 82, okay, here we haven't added semicolon, so I think this should be fine now. Still we have 2 errors. Before I is there, so let's recompile it and check it if it is working fine now. So we have received our output now. Now if you look at our output is printing elements 9, 7, 8, 1, 5 and 3. And deletion of elements is also happening according to their order. So 9 is getting deleted first, after 8, 7, 5, 3 and 1. So that means our elements are getting removed in proper order. Further, we can say that our program for priority queue implementation works fine. Now, if you guys are worried about this program, then not to worry. We have you covered. You can mention your email IDs in comment box below and we will send it over to you. Remember guys, we can make comments private to protect all your data. So you can fearlessly put all your email IDs in comment box below. Now we will discuss applications of priority queue to understand its importance. The first application that we are going to discuss is use of priority queue in Google Maps. You must have used Google Maps several times to navigate from one city to another or from your location to nearest desired location. Have you ever wondered how Google Maps managed to do that? How does it provide an optimal path to reach your location? Well, Dijkstra's shortest path algorithm implemented in Google Maps actually manages to do that by gaining access to all possible paths. This algorithm uses the priority queue to maintain all the paths in order. Let's understand how it works in detail. Now, when you provide the location of place you want to reach via your mobile device, Google Maps feeds the data of all possible paths to Dijkstra's algorithm. Those paths or road are stored in minimum priority queue considering the distance as parameter for priority assignment. And we have learned that the minimum priority queue maintains the lowest value at the front or root node. This is how the priority queue helps Google Map to search for an ideal path for reaching destination location. The next application that we are going to discuss is data compression in WinZip or gzip. These applications use Huffman encoding algorithm to reduce the size of files. Huffman coding is a lossless data compression algorithm, and in this algorithm, a variable length code is assigned to input different characters. The code length is related to how frequent characters are used. Most recurring characters have the smallest codes, and longer codes are for the least frequent characters. This is how the generated codes will maintain the complete data while utilizing less memory space. Let's understand how this process works with the help of an example. Let's say our text file contains these random characters. The Huffman encoding algorithm creates codes for each character based on its number of occurrences. For instance, the frequency of character A is more prominent than B, and character C has less frequency. So the length of code A is smaller than B, and length of code B will be smaller than C. Now, according to the amount of generated code, the priority queue will determine the priority of characters and will store them. These codes takes less size than the actual characters in memory space, and due to the mapping of occurrences, data does not get lost. I hope now you guys understand why the priority queue is treated as an abstract data structure itself and why it is the better version of queue data structure.
The stack is a linear data structure similar to arrays and linked lists, restricting the random access of elements. In the case of arrays or linked lists, you can access elements by either traversal or random indexing, which is reframed in stack data structure. You can understand a stack by visualizing it as a container of elements in which elements can only be placed on top of each other and removed from that same direction only. Stack as a data structure in computer science is not very different from stack as a way of organizing objects in the real world. So stack can be thought as the way you arrange books stacked on top of each other. These books can only be placed upon each other from the top end. Furthermore, to remove any particular book, you will first have to remove books stacked over it. This scenario accurately depicts sequential book access, equivalent to the stack data structure in computer science. The queue in data structure is also a linear data structure like a stack, having some restrictions on insertion and deletion. In the case of queue, insertion is performed from one end and the removal is performed from another or opposite end. The queue in data structure can be understood using the real-life example of a food court line. In any food court line or a movie ticket counter line, the customer who enters first always gets served at first, and the customer who enters last will absolutely get served at last. Furthermore, both the ends of these queues remain open, performing different operations. The rear end of the food court queue performs the insertion of a customer, whereas the front end performs the removal of the customer after providing him with the service that he desires. Both the stack and queue data structures follow the different operational principles to execute data manipulation operations. The stack data structure follows last in, first out, or first in, last out principles to execute its operations. In simpler words, the stack data structure removes the last inserted element at first and the first inserted element at last. Let's understand the principles mentioned above with the help of an example. As you can see in this example, 3 is the last inserted element, and if we start removing elements from this stack, 3 should get removed at first and 7 should get removed at last. Unlike stack, the queue data structure follows FIFO, which is the first in, first out principle, to execute its operations. According to this principle, the element which gets inserted in a list at first gets removed at first as well. For example, in this queue, 6 is the element which is inserted first. So, while performing the deletion, it should also get removed before all the other elements inside the queue. Moving forward, let's discuss different data manipulation operations for both of these data structures. The first parameter that we will talk about is the insertion operation. The process of inserting data entities in the stack is called a push operation. This operation can only be performed at the top end of a stack. For instance, consider the simulation of stack inserting few data elements. The elements that are getting inserted inside the stack are of homogeneous data type. Thus, we can say that stack can only store one type of data element. The insertion of elements in a queue data structure is referred to as an enqueue operation. It gets executed at the rear end of a queue. The simulation given in this section represents the execution of our enqueue operation. The next data manipulation operation we have on our list is deletion. The deletion of data entities from stack data structure is achieved using pop operation. The deletion of data entities from stack data structures is achieved using pop operation. This operation removes the elements where a top pointer is pointing. Thus, we can say that the stack performs the removal of data entities from its top end. This simulation shows how the removal of elements happens in the case of a stack data structure. Now, let's move to the deletion in queue data structure. The process of deleting data elements from the queue data structure is called dequeue. This operation is usually performed at the front end of a queue. The simulation given below represents how deletion happens from the front end of a queue, abiding with the first in, first out principle. Both of the data manipulation methods we reviewed earlier can be matched with previous real-life examples. What I mean by that is, the book stacking system can only place books at the top end as well as it can remove them from the top end only. Furthermore, the waiting queue analogy is deemed to be consistent with queue data structure because it adds people from the back end and removes them from the front end. Now here's the interesting question that we want y'all to answer. So until now we have understood the structural differences between stack and queue data structures, and both of these data structures can be implemented using static or dynamic data structures. So based on your comprehension of these data structures, which implementation strategy for constraint memory management is the best choice? The first option is array implementation static, and your second option is linked list implementation dynamic. Do think and answer. It will be interesting to see how many of y'all will get this right. So guys, leave your answers to this question in the comment section below. In a week's time, we will be announcing the right answer and y'all can check it out. So moving ahead, we will discuss about the pointers maintained in the case of both these data structures. For stack data structure, our ADI only remembers one location, that is the address of the topmost element. This tracking of a topmost element is achieved using one pointer, which we name as a top for our convenience. Whereas in the case of queue, we maintain two pointers named front and rear. The rear pointer points to the last inserted element in the queue, and the front pointer points to the first inserted element in the queue. We use and maintain these two pointers to execute different operations at both the front and rear ends. The last parameter that we have for differentiating stack and queues is when to use which data structure. The stack data structure is mainly used to solve problems that are recursive in nature. For example, memory management in programming environments. The resource allocation and execution of the programs is a repetitive process based on the invocation of different function calls. And stack is the basic memory management architecture for any modern computing environment. A stack is at the heart of the runtime environment for Java, C, C++, Ada, Fortran, and other languages, which is independent of their native codes like x86, Sun, or VAX. The stack memory management unit is compatible with old and new operating systems, including Windows NT 10, Solaris, and Linux runtime environments. The next applications of the stack on our list are expression handling and backtracking algorithms. The expression handling algorithms evaluates the output for arithmetic operation closed inside the parenthesis. The stack data structure is also used to perform expression conversions as infix to postfix, infix to prefix, postfix to infix, or prefix to infix. Furthermore, the backtracking algorithm is also implemented using a stack. This algorithm moves backwards and performs steps to evaluate a more adept solution. Now let's discuss about when to use queue data structure. The queue data structures work on sequential processing of data. Hence, whenever your application needs a sequential processing, a queue data structure can be implemented. For example, queue is used in messaging applications. You are probably aware that we all rely on messaging apps like WhatsApp, Facebook Messenger, and Instagram Chat to interact with our friends and family. And you must have noticed that the person you are attempting to communicate receives the messages in the same sequence as you have sent them, irrespective of whether he's online or offline. Actually, the queue is implemented in messaging applications at the user's end, containing the messages to be delivered to the user. So when the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. The next application of queue is its use in operating systems. Multi-user, multi-programming, and time-sharing environments are common in today's computers. In this OS setting, a system handles multiple jobs at once, and the concept of a queue is employed to manage these activities. So, remember guys, you can implement stack data structure to solve recursive problems and queue data structure to solve problems that need sequential data processing.
So what exactly is a tree data structure? The tree is a non-linear data structure that consists of nodes and is connected by edges. I know it's a little difficult to understand just by the definition, so let me show you the pictorial representation. As you can see, we have the elements, that is 10, 20, 30, 40, 50, 60, and 70, and all these are stored in the tree data structure. They are stored in a non-linear structure. If we had used arrays, it would have been in a linear consecutive way where 10 starts first and 70 ends at the last position. Now, in the next section, we will discuss why we had made to a switch to the tree data structure when we already had a linear data structure, that is array. Now the next topic, that is why we need tree data structure. So there are many reasons why we had switched into tree data structure, and one of the reasons is a linear data structure always stores the elements in a sequential form, that is, one after the other. And in operations to be performed in linear data structure, the time complexity increases as the data size increases. You can see here that, as discussed before, the elements are stored in a linear form, that is 10 at the first place and 70 at the last place. Imagine you wanted to access the element 70. Then using the traversal, you had to start from the first position, that is 10, 20, 30, 40, and slowly at the end is 70. So accessing that particular element is really time consuming. We are facing this just for 70 elements. Imagine if we had 700 elements, right? So that is exactly why we had made a switch to tree data structure. And using tree data structure, we have many advantages, as the tree data structure is completely non-linear and it allows easier access and quicker access of the data elements. How is that possible? We will look into it into the next segment, where we will discuss about the traversal of trees. Now, before we understand the traversal of trees, we should understand another important topic, that is the terminologies of tree. So, the first one is the node. Node is the entity that contains the keys and pointer to its child nodes. So here, you can see that the elements A, B, C, D, E, F and G are the elements. So each and every element, or the blue dot, is called as a node. And the blue dots here are 1, 2, 3, 4, 5, 6 and 7. So we have 7 blue dots. So we have 7 elements here. So you can see the line between each elements, right? So this particular line is called edge. Now we'll discuss about the edge in the next part. So the connecting links between any two nodes are called as edges. So we discussed about the nodes, right, where the element is stored. The blue dots are the nodes, and the lines connecting between the elements or nodes is called as the edge. So out of all the nodes, this first node, that is the element A, is called as the root node in a tree data structure. So indirectly, root node is also called as the parent node of all the nodes. Now we will understand what are parent nodes and children nodes. So in a tree data structure, the node, that is the node's predecessor, is called as parent node. So here we have discussed that A, or the root node, is the parent of all nodes. So for A, B and C nodes are children nodes. And for B and C nodes, A happens to be the parent node. Similarly, D and E are the children nodes of B, and F and G are children nodes of C. And the nodes D and E have B as the parent node, and the nodes F and G have C as the parent node. Now followed by that, we will understand the descendant node. So as discussed before, the descendant node is the node that comes after the parent node. Here, the B and C are the descendants of A, and D and E are descendants of B, and similarly F and G are the descendants or children of the node C. So in a tree data structure, the node which does not have any child is called as the leaf node. Now at the end we have D, E, F and G. So these particular nodes do not have any children nodes like B and C. So these particular 4 nodes which do not have any children are called as the leaf nodes. In a tree data structure, the node with at least one child node is called as the internal node. So here the internal nodes are B and C, which have at least one child. In a tree, the total number of children of a node are called as the degree of that node. So in this particular diagram, the degree of a root node is 2 because it has 2 child nodes, and the degree of B is 2 as it has 2 child nodes. Similarly, the degree of C is 2 because it has 2 child nodes. But when it comes to D, E, F and G, the degree is 0 because they do not have any child nodes. In a tree data structure, the root node is said to be at level 0, and the children of the root node are said to be at level 1, and the children nodes of the level 1 are at level 2. So to understand this, let's go through the diagram. As you can see, this particular root node is called as level 0. And followed by that, we have the children nodes of A, that is B and C, and that level is called as level 1. And followed by that, we have level 2. And if this tree goes forward, the levels also increase accordingly. Now, in a tree data structure, the total number of edges from a leaf node to the particular node is the longest path, and this particular path is called as the height of that node. Now here we have our general tree data structure, and here you can see the height of node A is 2. And the height of node B and C together is at 1. And the height of the last leaf nodes happens to be 0. Next, in the tree data structure, the total number of edges from the root node to a particular node is called as the depth of that node. Now in this particular tree data structure, the depth of the root node is 0. And the depth of B and C together is 1 because the number of edges connecting to the node A from B is just 1, and similarly the number of edges connecting the node C from A is just 1. So the depth of both B and C is 1. Now if we consider the last leaf nodes, then the depth is 2 because if you see, G is connected to A using 2 different edges. Similarly, F is connected to A using 2 different edges, and E and D also have 2 nodes to connect to A. So the depth is 2. Now in the next segment, we will understand the tree node. So the tree data structure has data part and references towards left and right child node in the tree data structure. So here you can see this is the node, and the node has 3 segments, that is data element and the references towards left child and the references towards right child. Now there are 4 different types of trees. The first one is the binary tree, followed by that we have the binary search tree, then we have AVL tree, and finally we have the B tree. Let us discuss each one of them. The first one is the binary tree. A binary tree is a tree data structure in which each parent node at most has 2 children. So in this particular tree, we'll have at most 2 children. That means it might have 1 or more than 1, but not more than 2 children per node. Moving ahead, we have the binary search tree. So a binary search tree or a BST is a tree data structure in which each node has a maximum of 2 children. All nodes of the left subtree are less than the right node. All nodes on the right subtree are more than the root node. So here you can see the image or the GIF which represents the image of a binary search tree. So here, all the nodes of the left subtree are less than the root node and all the nodes of the right subtree are more than the root node. The next type of the tree is the AVL tree. The AVL tree got its name after inventory Georgi, Adelson, Welsky and Landis. AVL tree is the self-balancing tree in which each node maintains a balance factor whose value is either 1, 0 or -1. Balance factor is equals to height of the left subtree minus height of the right subtree, or height of the right subtree minus height of the left subtree. So in this particular image, you can identify it is an AVL tree. And now the last type of tree, that is the B tree. B tree is a special kind of self-balancing search tree in which each node can contain more than 1 key and can have more than 2 children. B tree is also known as the height-balanced M-way tree. Now in this particular GIF, we can see how a B tree looks like. Now followed by this, we will discuss the tree traversal. So traversing a tree helps to visit required node in the tree to perform specific operations. Tree traversal can be performed in 3 different ways. The first one is the pre-order traversal, where we visit the node and visit all the nodes from the left side, then visit all the nodes from the right side. So this particular GIF is an example for pre-order traversal, where we visit all the left side nodes first, then we visit the right side nodes. Now we will move ahead into the next type of traversal. That is the in-order traversal. First, we visit all the nodes from the left side, then we visit the root node, and then we visit all the nodes from the right side. So this particular GIF will be an example for the in-order traversal, where we visit all the left side nodes, then we visit the root node, and followed by that we will visit the right side nodes. And the last type of traversal is the post-order traversal, where we visit all the nodes from the left side first, then we visit all the nodes from the right side, and finally visit the root node. So this particular image on the right side is an example for post-order traversal. Now before we get into learning the applications of trees, we will try to execute one example based on the post-order, pre-order and in-order traversals in tree data structure. So you can see that we have an example on my screen right now. So here we have the node structure, then we have the in-order traversal function, followed by that we have the pre-order traversal function, and finally we have the post-order traversal function. Now let's quickly run this program and see the output, and don't worry about the code. This particular code document will be attached in the description box below and you can have access to it. Now we have the run option over here and the program got successfully executed. You can ignore this warning, and here we have the in-order traversal of the tree and the first output. Then we have the pre-order traversal of the tree, and finally we have the post-order traversal of the tree. Now let's discuss the last part, where we will learn the application of trees. So the application of trees are as follows. Binary search trees are used to quickly check whether an element is present in the set or not. Then we have the most popular database usage of B-tree, which is a variant of tree data structure. Then we have the modified version of trees called as Tress, which is used in the router to store routing information. And finally, the compiler uses a syntax tree to validate the syntax of every program you write. So it is a tree data structure in which each node can have at most 2 child nodes. These nodes are referred to as left child node and right child node. Next, let's discuss about some terms related to binary tree. First up, a node. A node consists of data and a link to its both child nodes. Next, the root node. Root node is the first node of the tree. Next, leaf nodes. These are the nodes which has no child. Next, parent node. Apart from the root node, any node which has at least one child is called as parent to that child node. Next up, a child node. Any node with a parent is called as a child node. Next up is the internal node. Any node with a child and a parent is called as an internal node. Next up is the height of the binary tree. The longest path from the root to any leaf node is called as the height of the binary tree. Next up is the depth of the binary tree. The depth of the node is the total number of edges from the root node to the target node or the last child node. Now let's try to implement the binary tree in the code editor. As you can see, now we are on the code editor, and the code on my screen is an example for binary tree. Now here you can see that we have created a structure for node, followed by that we have a function where we will print the tree, and this is our main function. Now don't worry about the code, this particular code segment will be available in our description box below, and you can always have access to it and try to edit and run this code on your own local system to have a better learning experience. Now without further ado, let's try to run this program quickly and see the output. So there you go, the code got successfully executed, and here you can see the output of this particular binary tree. Now let's get back to the theory part. So as discussed before, followed by the implementation part, we will learn about the properties of a binary tree. Now let's discuss the properties of the binary trees. First up, maximum number of nodes at a level L is 2 to the power L. Next up, maximum number of nodes in a binary tree of height h is equals to 2 to the power of h minus 1. Next up, minimum possible height in a binary tree with 2 nodes is equals to log of L plus 1 base 2. Next up, the minimum possible level in a binary tree with n nodes is equals to log of L plus 1 base 2. Finally, a binary tree with L leaves has at least log L base 2 plus 1 levels. Now, let's discuss about the different types of binary trees. First up, we have the full binary tree. Followed by that, we have the complete binary tree. Then we have the perfect binary tree. Followed by that, we have the balanced binary tree. And lastly, the degenerate binary tree. Let's discuss about these in detail. First up, full binary tree. A full binary tree is a unique tree data structure in which a node can have either 2 children or no child. Next, a complete binary tree. So a complete binary tree is another specific binary tree where each node on all levels except the last level must have 2 children, and at the lowest level, all leaves should reside possibly on the left side. The next one is the perfect binary tree. A binary tree is perfect if every node must have 2 children and every leaf is on the same level. The next one is called as the balanced binary tree. A binary tree is balanced if, for each node, the height of the left subtree and the height of the right subtree varies at most by just 1. At last, we have the degenerate binary tree. A binary tree is said to be degenerate if every internal node has only one child. We have now discussed the binary tree, some terms and properties related to binary trees, and types of binary trees.
Now we will look into the operations that needs to be performed on the binary tree. So there are basically 3 types of operations that can be performed on binary tree, which are traversal, insertion, and deletion. So first we'll look into the traversal operations. There are 3 different types of traversal operations possible on binary tree, which are pre-order traversal, in-order traversal, and finally the post-order traversal. Now let's get back into the text editor mode and try to execute our example. So right now we are on the text editor, and this particular code is for the traversal operations on our binary tree. And here you can see we have the structure for node, and we have also the in-order function, pre-order function, and post-order function. And don't worry about the code. This particular code will be available in the description box below. And after you have written the code, we have some standard input over here. You can see that we are giving the number of edges as 4, and the left subtree elements are 2 and 1, and the right subtree elements are 2 and 3, and another left subtree elements are 3 and 5, and lastly we have 5 and 6 for another left subtree. Now let's try to execute this code. Now we have already executed the code, and we also have the output over here, and here you can see we have entered the number of edges as 4, and the traversal is in-order traversal, which is 1, 2, 6, 5 and 3, and the pre-order traversal output is 2, 1, 3, 5, 6, and the post-order traversal is 1, 6, 5, 3 and 2. Now let's get back to the PPT. Now we have the insertion operation. And now let's get back to our text editor and try to see an example for insertion operation as well. So on my screen you can see an example for insertion operation. So here we have the insert function. As I said, this particular code will be available in the description box below. Now let's provide the standard input. So the standard input will be 4 edges, and we have 2 and 1 as the left subtree, and 2 and 3 as right subtree, 3 and 5 as left subtree again, and 5 and 6 as the left subtree. Now let's quickly run this code, and there you go, the program got successfully executed, and here we have the output. The nodes got inserted, and it has provided an in-order traversal, that is 1, 2, 6, 5 and 3. Now let's get back to the presentation, and the last type of operation is the deletion operation. Let's quickly execute an example based on deletion operation as well. Now as you can see, we are on the text editor again. Now here the example is for deletion operation. We have the delete function over here. Now for this particular program we don't need any standard inputs, so just let's run the program. So there you go, the program got successfully executed, and we have the output over here. And in order traversal before deletion, and in order traversal after the deletion of an element. So the deleted element is element 11. Now with that, let's get back to the presentation mode again. So that's how the element got deleted. Now we have reached to the last part of this session, that happens to be the final key takeaways. So what are the final takeaways? So binary tree is faster at search operations than other type of tree, and it is easier to find maximum and minimum elements in the binary tree. Binary tree does not allow duplicate values, and graph traversal is done using binary tree. It is used to convert the postfix expressions into the prefix expressions. So these were the final takeaways. Tree traversal is a process of visiting each and every node in a tree data structure. So right here on my screen, we have a tree with different nodes, that is A, B, C, D and E. So here we will be visiting all the nodes one after the other using the tree traversal methods. Now that we have a brief understanding of what exactly is a tree traversal process, let's get into the next topic of our discussion for today, that is the data structure used for tree traversal. In a tree data structure, there are primarily two data structures utilized for tree traversal. The first one is the stack data structure and the second one is the queue data structure. A stack is a linear data structure that operates on the last in, first out, LIFO principle. There is only one pointer in the stack, that is the top pointer, which points to the stack's topmost element. Only the top of the stack is used for insertion and deletion. Now the next one is the queue. A queue, unlike stacks, is open on both the ends. The one end is always open and used only for input and the other is only used for deletion or elimination. The principle followed in queue is first in, first out or FIFO approach. Followed by that, we will look into the different types of tree traversals in data structure. Tree traversal can be done in the following ways. The first one is breadth first search and the second one is the depth first search. First, let us have a look at the breadth first search algorithm or breadth first search traversal. We follow level order traversal in breadth first search. Breadth first search traverses nodes by level instead of subtrees. First, we visit the root node. Followed by the root node, we visit the left subtree of the tree. Then, followed by the left subtree, we finish the right subtree of the entire tree. After that, we go until the leaf nodes of the entire tree is found. The second one is the depth first search. In depth first search, we traverse tree data structure in three ways, that is pre-order traversal, in-order traversal and post-order traversal. Let us take a look at how these traversals are carried out. First, let us discuss the pre-order traversal. We traverse the root node first in the pre-order traversal. Then we traverse through the left subtree and finally we traverse through the right subtree. Then there is in-order traversal. In-order traversal involves traversing of the left subtree first, followed by that we enter the root node, then we visit the right subtree. Lastly, we have the post-order traversal. So post-order traversal involves traversing of left subtree first, then the right subtree, and finally we visit the root node. Now next, we will have a look at some of the important applications of tree traversal in data structure. So we use tree traversal in data structures to build a prefix expression or Polish notation from expression trees. Then utilize the pre-order traversal and then traverse the expression tree in a pre-orderly manner. A binary tree's postfix representation or reverse Polish notation can be generated using post-order traversal. Because it returns values from the underlying set in order, according to the comparator setting up the binary search tree, in order traversal is often employed on binary search trees. A complete binary tree can be deleted or released when deleting or freezing nodes and values in the post-order traversal. Now, next we will see an example based on tree traversal in data structures.
So on my screen we have an example for tree traversal in data structure. To begin, we have included the enum or user specified data type traversal. It mostly used to give integral constant names which make a programmer easier to comprehend and maintain. We defined three variables in the enum data type, that is pre-order, in-order and post-order traversal. We can define the type that can take one of the two values by using the typedef and enum keywords. We have a traversal data type with trav variable and a node data type with node variable. Then we define the node using the data structure type as struct node. We declare one variable x and two nodes as a left and a right nodes respectively in this node section. We then attempted to create a node using the create node function, passing the root node as an argument. In this code, we use a malloc function to create a node, assign data to x and null to both the right and left nodes before returning to the root node. If node t is not equal to null, we simply return it. Otherwise, we will use the released tree function to release the left and right nodes. And if neither is a root node, then we will use the free function to release the node T, which will behave as the root node. Then we define the display tree function, which takes the trav variable and the root node as parameters. There is a condition in this function, that is, if the root node is not null, we will return the root node. Then, using the switch case scenario, we attempted to traverse the tree using all three types of traversals. We utilize a trav variable in the switch function, so if any of the in-order, pre-order or post-order variables match the trav variable, the traversal will be executed. Then, we created a tree using the createTree function, which takes a data variable as input. In the createTree function, we used a malloc function to create the root node, and we first assigned null to the left and right nodes, as well as the data to the variable x before returning to the root node. We first traversed the root node, then the left subtree, and finally the right subtree in the pre-order traversal case. In order traversal case, we first traverse the left subtree, then the root node, and finally the right subtree. And in the post-order traversal case, we traverse the left subtree, then the right subtree, and finally traverse through the root node. And finally, we exit the display tree function and moved on to the main function. We assign the values 5 as the root node, then 10, 20, and 30 as the left nodes, and similarly 15, 25, and 35 as the right nodes, and then we call the three tree traversals, that is pre-order, in-order, and post-order, to traverse the tree. And finally, we release the root node. Now, let us try to execute this program and see the output. So there you go. The program got successfully executed, and you can see that the output has been displayed on my screen. So the pre-order traversal is 5, 10, 20, 25, 15, 30, and 35. Followed by the pre-order traversal, we have the in-order traversal, that is 20, 10, 25, 5, 30, 15, and 35. And finally, we have the post-order traversal, that is 20, 25, 10, 30, 35, 15, and 5.
So without any further ado, let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion. We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, right. Next, we will define some functions publicly. Public First, default constructor. And a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructor's definition. So bst Now let's write the parameterized constructor's definition. Bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst bst star root comma int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise we will insert the data. So if the value is greater than root data, then we have to insert it in the right subtree. So root right is equals to insert root right comma value. Else else the value should be inserted in the left side. So root left is equals to insert root left comma value. And then we will return root. Now let's write the traverse function. So void tst traverse tst star root. If root then we will return otherwise we will first traverse left side then we will print the root data. And then we will traverse the right side root right. Now let's write the main block. So we will start with an empty tree. So bst b comma star root is equals to null. The root is equals to b dot insert root comma 50. B dot insert equals to root comma 10. B dot insert gonna be root comma 30. B dot insert gonna be root comma 50. Sorry, we already used 50, so we will use 60. B dot insert root comma let's use 20. Let's try to traverse this. So B dot traverse root. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides. At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor. Let's start by creating a node. This time we will use structure. So struct node
int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree. Traverse struct node star root. So if root is equals to null, so traverse root left cout root e traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and parents left is not equals to null, so current should be equals to current to return current. Struct node star delete node struct node star root comma int key. If root equals to null, return root. Now, if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left, it will be equals to delete node root left key. Comma key. Now if the key is deleted is greater than the root key, then it lies in the right subtree. So else if key is greater than root, root right is equals to delete node root right comma key. Else if roots dot left equals to null and root dot right is equals to null, then return null. Else if root left equals to null, then struct node star temp is equals to root right and free root. Return temp. Else if roots right is equals to null, then struct node star temp is equals to root free root. Return temp. Now node with the two children get the in-order successor smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successor's content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp p. Now we will return root. Now let's write the main block. We will start with an empty tree struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root comma 3 root is equals to insert root comma 4 root is equals to insert root comma 7 and root equals to insert root comma 6. Let's try to traverse this. So cout traversal of the given tree traverse root. Now first we will delete a value. So cout delete 2 now root is equals to delete node root comma 2 or cout. Traversal after deleting the traverse route. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get back to our slides.
At last, let's sum up what we have learned from this session. First up, left side nodes are always lesser than the parent's node, and the right side node are always more than the parent node. Next, it is easier to search and sort elements in a binary search tree. Finally, a binary search tree offers faster insertion and deletion operations. So let's get started with introduction to AVL trees. An AVL tree is a height balanced binary search tree. For each node, we have to make sure that the height of the left subtree and the right subtree can differ by at most 1. We can calculate this balance factor by subtracting the height of the left subtree from the height of the right subtree. Now let's discuss various rotations we can perform on AVL trees. First up, LL rotation. Next, RR rotations. Next, LR rotation. At last, RL rotation. Let's discuss them in detail. First up, LL rotation. It is a clockwise rotation when a node is inserted on the left subtree of the left subtree of a node. Then we apply this rotation to balance the tree. It is applied on the node below the balance factor 2 node. That is, we will apply right rotation on the green node. Next, RR rotation. When a node is inserted into a right subtree of the right subtree of a node, then we perform RR rotation. It is an anti-clockwise rotation which is applied on the node below a node having balance factor -2. That is, we will apply it on the green node. Next up, LR rotation. When a node is inserted into right subtree of the left subtree of a node, then we perform LR rotation. It is a combination of RR and LL rotation. First, we will apply RR rotation on green and yellow node. After this, red node is still unbalanced, so we will perform LL rotation on the yellow node. Finally, RL rotation. When a node is inserted into the left subtree of a right subtree of a node, then we perform RL rotation. It is a combination of LL and RR rotation. First, we will apply LL rotation on green and yellow nodes. After this, the red node is still unbalanced, so we will perform RR rotation on the yellow node. Now, let's discuss complexity of AVL trees. First up, space complexity is a big O of n. Next up, AVL tree offers a complexity of big O of log n for searching. Next up, AVL trees offer a complexity of big O of log n for insertion. Finally, AVL tree offers a complexity of big O of log n for deletion. We have now introduced an AVL tree and rotations on it. Now, let's discuss some of the operations we can perform on AVL trees. First up, insertion and deletion. Let's discuss them in detail. First up, insertion. We will insert a node following binary search tree rules. Then we will check if the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor.
Let's start by creating a node. To create a node, we need a class node. We will create its member as public int key node star left node star right int height. Now let's write a function to get maximum of two integers. So int max int a comma int b. Now let's declare a utility function to get maximum of two integers. So int max a comma int b. Now let's write a function to get the height of the tree. Int height node star n. Now if n is null, then we will return 0. Else we will return n calls height. Now let's write that function to get maximum of two integers. Int max int a comma int b. We will return if a is greater than b, then we will return a, else we will return b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. Node star node equals to new node. So node key will be equals to key node left will be equals to left. Node left will be equals to null and node right will be equals to null and node height will be equals to 1. And return node. Here we have kept height as 1 because at the new node is initially added at leaf. So by default it will always be at 1. Now let's write a utility function to right rotate subtree rooted with y. Node star right node star y. Now node star x is equals to y's left and node star t2 is equals to x right. Now we will perform rotation. So x right will become y and y's left will become t2. Now we will update the heights. So y height is equals to max of height of y left comma height of y right. Plus 1. Now x height equals to maximum of height x left comma height of x right. Plus 1. Now return x Now let's write a utility function to left rotate subtree rooted with x. So node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to axis y's. Now we will perform rotation. So y left will be equals to x and x right will be equals to t2. Now let's update height. So x height is equals to maximum of height of axis left comma height of axis right and y's height is equals to maximum of height of y's left comma height of y's right. return y. Now let's write a function to get balance factor of node n. So int get balance, argument as node pointer n. If n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a recursive function to insert a key in the subtree rooted with node and returns the new root of the subtree. So node star insert node star node comma int key. Now we will perform the normal BST insertion. So if node is equals to null, then we will return new node key. Now if this key is less than node's key, then node left will equals to insert node left comma key. Or else we will insert that in the right. Node right is equals to insert node right comma key. Now we will return node. This if else will make sure that we will reach to the leaf node and then we will insert the key. Now we will update the height of this ancestor node. So node height is equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor for this ancestor node to check whether this node became unbalanced. So int balance is equals to get balance. Now if this node becomes unbalanced, then there are four cases. So if balance is greater than 1 and key is less than node left key, then we will return right rotate node. This if statement for the left case, so or LL case. Now let's write it for the right case or RR case. So if balance is less than -1 and E is greater than node right key, then we will return left rotate node. Now write for the left right case or LR case. So if balance is greater than 1 and key is greater than node left key, then node left is equals to left rotate node left. Now return right rotate. Now let's write the right left case or RL case. So if balance is less than -1 and key is less than node to the right key, then node right will be equals to right rotate node to the right, and we will return left rotate. Now we will return this node. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So now if root is not null, then cout root key and now pre-order root. And pre-order Now let's write the code for the main block. We will start with an empty tree. Node star root is equals to null. Now we will try to construct tree. So root is equals to insert root comma 10. Now root is equals to insert root comma 5. Root is equals to insert root comma 2. Root is equals to insert root comma 3. Root is equals to insert root comma 7 and root is equals to insert comma 9. Now let's try to print this tree. So cout avial tree is equals to tree in pre-order pre-order root. Let's execute this. As you can see, we have successfully created our first avial tree. Let's get back to slides. At last, deletion. We will delete a node following a binary search tree rules. Then we will check if all the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will define its members as public int key node star left node star right int height Now let's write a utility function to get height of the tree. So int height node star n. If n is equals to null, then in that case we will return 0. Otherwise we will return n's height. Now let's write a utility function to get maximum of two integers. Int max int a comma int b. So we will return if a is greater than b, then a, else b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. So node star new node is equals to new node parenthesis. Now new node will get key as key. New node left is equals to null, and new node right is equals to null, and new node's height is equals to 1, because new node is initially added as leaf. That's why it is always be given as 1. Now we will return this node. Return node. Now let's write a utility function to right rotate a subtree rooted with y. So node star right rotate node star y. Node star x is equals to y left node star t2 is equals to x right. Now we will perform rotation. So x right is equals to y left is equals to t2. Now we will update heights. So y height equals to maximum of height of y's left comma height of y's right plus 1, and x height is equals to maximum of height of x's left comma access right plus 1. Now we will return this new root. So return x. Now we will write node star left rotate node star x node star y will be equals to access right and node star t2 will be equals to y's left. Now we will perform rotation. So y left equals to x and x right is equals to t2. Now we will update these heights. So x height is equals to maximum of height of x left comma height of x right plus 1 and y's height is equals to max of height of y's left comma height of y's right plus 1. Now we will return this y. Now we will write a function to get balance factor of node n. So int get balance node star n. So if n is equals to null, then we will return 0. Otherwise we will return height of n's left minus height of n's right. Now let's write a function to insert a node. So node star insert node star node comma int key. Now we will perform normal BST rotation. So if node is equals to null, then we will return new node key. So now if key is less than node key, then node left will be equals to insert node left comma key. Now if key is greater than node key, then node right is equals to insert node right comma key. Else we will return node because equal keys are not allowed. Now we will update the height of the ancestor node. So node height equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor of this ancestor node to check whether this node becomes unbalanced. So if int balance equals to get balance of this node. Now if this node becomes unbalanced, then there are 4 cases that could be possible. First up, LL case. So if balance is greater than 1 and key is less than node left key. Return right rotate node. Now let's write right case. So if balance is less than -1 and key is greater than node right key, then we will return left rotate node. Now let's write left right case. So if balance is greater than 1 and key is greater than node left key, then node left will be equals to left rotate node, and we will return right, rotate, node. Now let's write the case for right left case. If balance is less than -1 and key is less than node right, so node right is equals to right rotate node right. Now we will return left rotate node. Now let's return the unchanged node pointer. So return node. Now let's write a function to find minimum value node. So node star min value node, node star node. So node star current equals to node. So while current left is not equals to null, current is equals to current at left. Now we will return current. Now we will write a recursive function to delete a node with the given key from subtree with the given root. So node star delete node. Its arguments are node pointer root, comma, int key. For starters, we will perform standard BST delete. So if root is equals to null, then we will return root. Now, if the key to be deleted is smaller than the root key, then it lies in the left subtree. So, if key is less than root key, then root left will be equals to delete node root to the left, comma, key. Now, if key to be deleted is greater than the root key, then it lies in the right subtree. So else if key is greater than root key, then root right equals to delete node root right comma key. Now if the key is same as the root key, then this is the node to be deleted. So else if root left equals to null or root to the right is equals to null, then node star temp is equals to root left now if temp is equals to null, then temp will be equals to root and root will equals to null. Else root will be equals to star temp and free temp. Else node star temp is equals to min value node root right Now we will copy the in order successors data to this node. So root e is equals to temp key. Now we will delete this in order successor. So root right is equals to delete node root comma temp key. Now if root is equals to null, then we will return root. Now we will update the height of the current node. So root height is equals to 1 plus max of height of roots left, comma height of comma height of root right. Now we will get the balance factor of this node. So int balance is equals to get balance root. If this node becomes unbalanced, then there are 4 cases. First up, LL case. So if balance is greater than 1 and get balance of roots left is greater than equals to 0, then we will return right rotate. Now if balance is greater than 1 and get balance of root left less than 0, then root left will equals to left rotate root left. Now we will return right rotate root. Now let's write right case. So if balance less than -1 and get balance is less than equals to 0, Then we will return left rotate now we will write right left case. So if balance is less than -1 and get balance of root right is greater than 0, then root right is equals to right rotate of root right. Now we will return left rotate and we will return this root. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So if root not equals to null, then cout root e a pre-order root left and pre-order root right. Now let's write a code for the main block. We will start with an empty tree. So node root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 10 root is equals to insert root comma 9 root is equals to insert root comma 7 root is equals to insert root comma 5 root is equals to insert root comma 3. Now let's try and print this AVL tree. So cout created AVL pre-order pre-order Now we will delete a node. So root is equals to delete node root comma done. Now let's again try and print this. So cout modified behavior tree pre-order after deletion of 10. Out handle pre-order root read. Now let's execute this. As you can see, our deletion function is working perfectly.
So with this, we have come to the end of the session on the data structures full course. I hope the session was informative and interesting. If you have any queries regarding any of the topics covered in this session, or if you require the resources like PPT, code documents or anything, then please feel free to let us know in the comment section below, and a team of experts will be more than happy to resolve all your queries at the earliest. Until next time, thank you, stay safe and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.